Hi guys, name's Louis Best. As you know, the project is Titan Rover, so today we're just going to go over a preliminary design review, and in the interest of time, we're going to be starting off a little bit quick in terms of what the project's requirements are. So first and foremost, obviously, Titan Rover main objective is to compete in the University Rover Challenge. It's an international competition played by Mars Society at the MPRS site outside of Hanksville, Utah. The main goal is to be able to create a robust teleoperated platform working on the first inhabitant of Mars in a series of tasks. Those tasks include equipment servicing, where the rover is going to need to be able to pick up a series of objects to include tools and toolboxes, as well as then work on a analog lander, operating things like switches, levers, knobs, typing on a keyboard, replacing electronic component boards. Following on from that is extreme delivery and retrieval, where our rover is tasked to pick up objects of interest, whether that be tools or forms of water bottles to assist fallen astronauts, traversing across extremely hazardous terrain, getting from essentially one point to another. From there, our science cache, which is where this year we'll be expected to be able to sample up to 6 soil sites, as well as doing geological analysis on site from the rover. And our autonomous traversal task, which requires to be able to, as it is name implies, traverse autonomously from one point to another, given a set of coordinates by competition. So what that means in terms of what our system requires overall is that we need a versatile suspension, given the desert terrain, the rocky desert terrain out there in Hanksville, Utah. We need to have a robotic arm capable of manipulating objects within its work envelope. We need to have an electrical distribution system to distribute power to every onboard component and computer system. We need to have a communication system so that we can teleoperate this rover from our base station up to 1 kilometer away. We need to have a controls graphic user interface so that way our team knows not only the inputs going to the motors on board the rover, but also the feedback that we get from them, as well as the camera systems we have so we know where we are and where we're going. And the science cache, which is part of our laboratory analysis here. What that means in terms of design parameters has to do that obviously we need an off-the-grid teleoperated platform. This year we do need to fit within 1.2 square meters for a weigh-in. We are allowed to disassemble our rover, though there are a few components that still need to meet this criteria. Our entire system must be under 50 kilograms per configuration for a task, and if we were to put all systems on board the rover at once, it may never exceed 70 kilograms. The cost of the total system, including the base station, must not exceed $18,000. It must be field serviceable, given that we're expecting to have complications and need to make adjustments overnight before our next task, as well as have a rapid deployment, as we only have 15 minutes of setup time to then compete. So that being said, I'm going to now introduce my mechanical design lead, Nguyen.
How do we define rapid deployment? Is there a minimum delta T that we have to hit?
So rapid deployment for us is essentially because we have to transport the rover from our base camp to the actual competition site. Traditionally, what we try to do is have as many systems on the rover set up as possible, but there are still things such as power sources, or sometimes during certain tasks, for example, the robotic arm, that when we get there, we want to have as few mounting points as possible per system so that they can be quickly assembled and deployed.
Yeah, do we have a minimum how much time we have to hit?
Yeah, 15 minutes is the setup time typically. You are allowed to exceed that, though it will eat into your task time, and if you run out of task time, you run out of task time.
15 minutes.
Yes. Apologies.
Okay, so I'm just going to go quickly over the mechanical system overview. So the rover must utilize the power system that's applicable to the Martian environment, which means that the system might not be able to ingest ambient air for combustion, traverse over rugged terrains, manipulate any objects within its work envelope, collect soil samples for science analysis, onboard analysis, and relay the data back to its base station. The rover must not weigh more than 88 pounds. That's for the mechanical system, and must cost no more than $12,000. Here's the breakdown of the weights and budget. Sorry for the typo. Chassis should be, for the money, it should be about $500 and less than 10 pounds. And science should be $4,000 and less than 38 pounds. And it must fit a 1.2 square meter platforms, and it can be disassembled during this time to weight.
How you doing, everyone? My name's Aaron Hernandez. In case you're found, this is chassis lead, and joining me is Gabriel, and we're gonna go over the chassis system. Chassis system essentially encompasses the chassis platform itself as well as the antennas. So we're going to talk about the chassis first. So for our problem description, we are seeking validation for utilizing last year's chassis platform. Some of the requirements that go along with the chassis is that the chassis needs to withstand the forces exerted from all subsystems. It also needs to maintain a high life cycle in order for us to ensure that it is maintainable and maintains its functional performance. The chassis also needs to house all electrical and controls components so it can be functional, and it needs to also tolerate any generated tear-out scenarios.
What's a tear-out scenario?
A tear-out scenario is essentially when we have a fastener somewhere in our system, and the shear force is actually, the shear force exerted on that bolt does not necessarily shear the bolt itself, but it shears the fastener out of the tube.
Your high cycle, how many cycles?
So that will be in the performance criteria that we're aiming above 1,000 cycles.
How many cycles has the chassis already experienced?
That is
No, doesn't achieve that. So I think you have to consider that.
So our design parameters for the finite life cycle, please excuse the typo for the first arrow. That does not fall under the requirements of the life cycle. The first requirement is that first parameter is that the load produced from the other subsystems. These load values have a direct correlation to what kind of cycles we will be, or what kind of output cycles we will notice from the chassis. Also the type of loading, whether it be bending or axial, those factors have also a direct relationship as to how many cycles this portion of the scenario will survive. Our reliability factor KE, essentially how responsive or how consistent we want to see in the results of the loads experienced in these different scenarios. And then our loading factor K is also related to what type of loading, whether that be bending or axial. And then for full tear, the parameters that go along with that are essentially the hardware size as well as the hardware grade and the relative position of those fasteners in the chassis. So as I stated a little bit earlier, our performance criteria for the finite life cycle, we want to aim above 1,000 cycles since we want essentially the system to be extremely reliable and maintain its functionality.
How do you compute a life cycle? What dictates a cycle?
Essentially, a cycle consists of the amount of times that the system is induced by a load within a certain scenario. We have 4 different scenarios. However, a life cycle can be computed and determined by the stress that's induced on that portion of the system.
So we anticipate, let's say we go and test the road for 10 minutes. Is there a certain number of cycles that goes on?
Absolutely. Basically, at the
Do you
end,
have like a number that you kind of identified?
determining on
Would you
when we
estimate?
test.
Yeah, would you estimate how many load cycles happen based on?
Essentially, the way we set it up is essentially whenever, because we base this off the worst case scenario. So we would consider, in this case, 1 cycle to be the worst case scenario. Let's say the rover falls a 1 meter drop and the whole location for the shock mount experience a total of 800 pounds of force. That would be 1 cycle. So as you can see, our governing equation for our finite life cycle consists of N, or is N, and consists of our von Mises stress as well as computing our design factor. Our reliability factor KE is going to be 99.99%, essentially because we want to aim high for the overall reliability of the system, so that way we don't have any failures. And that correlates to a 0.7 value constant. Our loading factor KC will depend on what type of load we have, whether it be bending or axial. You can see the values as follows. We also need to calculate the endurance limit. We need to calculate the endurance limit so we can see the expressions and all the, and these expressions will essentially describe the behavior of the material under these certain conditions. And then we have essentially our von Mises stress and our fatigue fracture constant, which is associated to theoretical value for 66.96. And we must also compute compute our constants A and B, which correlate directly to the life cycle equation. So for our first analysis, we're analyzing the hole locations on the shock mount. So we essentially have two shocks. We have a double wishbone system, and on the shock hole locations, we are essentially experiencing two outputs, shock 1 and shock 2. This totals out to be an 800 pounds of force exerted on those shock holes. From our computation results, as you can see, A and B were determined, and our design factor came out to be 3.1. As you can see, the number of cycles that we've computed is 105 times 10 to the third cycles. So from this result, we've determined that this cycle now meets our requirements for performance criteria.
So is this for the tear out situation or the bending of the bar?
Essentially the bending of the bar, the stress is
Right.
For the second analysis, the science auger system, we realized that the science auger system does not experience or output any significant types of loading. Hence, as you can see, the high cycle output value that we're receiving. Essentially, the system itself distributes a load across these 6 fastening locations at 20 pounds of force. Hence, why we have such a high design factor and a high number of cycles.
So Ben, why do you have 6 bolts? Is that the minimum number that we need to support for?
So the 6 hole location was actually, they're basically hole locations that were used for last year's auger system, and this year's auger system is going to be very similar. So our team plans on utilizing those same hole locations for the ideal purpose location.
Are you assuming they're all evenly distributed?
Yes.
That may not be the case simply because you may have some top ones may take more than the other ones based on the bending and the moment produced by the weight of the auger system. So some may be more loaded than others. Right now, if you were to do an analysis, it's an over-constraint problem. You want to make it easy, assume all 3 of them are 1 bolt, bottom ones are 1 bolt, do it 2 points, do a bending moment about it, and force it into Y, and then evenly distribute it. But between the top and the bottom, I would expect a different load based on the fact that you have the moment induced by the weight of the auger system. Second, when the auger is drilling, it may have a separate reactive force pushing on it. So you've got to look at those scenarios. I don't know, is this for bending of this chassis, or are we looking at the tear out scenario?
This we're essentially looking at the shear, cosmetic weight.
So if you're looking, at the shear, you definitely want that. That's basically a part, not bending of the added shear there locally. On the previous one, you said you're looking at the bending of it, but are you looking at the tear out?
No.
Because you have a really thin wall and you have 400 pounds of force shearing through it. I mean, I think that'd be a much more critical thing to look at. Or you may have even, maybe not tearing it up, you may yield it. You may make that circular hole into a slotted hole because it's locally yielding. Factor that with the fact that you have stress concentration added in there, you could ultimately shear out the hole. Because 400 pounds seems like a lot. I don't know where that number came from. It seems like a lot.
That's a calculated by the receiver analysis from our mobility.
It's also a worst case scenario analysis. So that's part of what both chassis anticipation is, that we are analyzing system capability in worst case scenarios.
Road falling on one wheel. All right, that makes more sense. I would imagine that you'd still have, they would be different in magnitude. Go back. Let's say that impulse force is 800 pounds. Well, this is 2, but one wheel takes it. Those bolts. Let's say the top right wheel hits the ground first on impact. Those 2 bolts will not have the same force loading on it. I would imagine something asymmetric. And again, you'll isolate worst case scenario by isolating one of like asymmetric loading. Symmetry is too likely. Right now, it seems like it's hitting both wheels versus one wheel. And I think you're more likely to hit one wheel, especially any potential rotation due to the asymmetric loading or the arm being off to one side, so the CG lost that, so it rotates a little bit. I think that's more likely to happen.
So for our next analysis, the robotic arm. So the robotic arm itself induces a moment of 2,000 pound-inches at the center of the two horizontal members that you see in the free body diagram. They also induce opposite force reaction, which generates the moment. From our calculations, we completed design factor of 3.2, and the cycles that we computed are 475, which also meets our performance criteria. For our last analysis, the control arm impact. So in this scenario, essentially the rover, if the rover were to experience any sort of impact at its maximum velocity, running into an object and the first point of contact being the tire, it would then generate a force that's transferred up to the control arms and then induce a moment to the fastened position on the chassis as you see in the diagram. And this will then generate a moment which equates to 7,062 pound-inches. From this result, we then computed a life cycle of 24/7 cycles. As you can see, the life cycle computation is low. However, we are perfectly fine with this result due to the fact that whenever the rover is in operation, we always have a essentially a body, if you will, next to the rover while it is in operation for any sort of emergency in order to kill power if we were to lose control.
So we're doing about 600 horsepower.
Yes, at our maximum velocity if we were to fly with any object.
The arm is fully extended.
No, the arm is essentially in a stationary position.
Oh, I see. Oh, the control arm. How fast are we moving?
Maximum velocity it would approximately be 13 miles per
Like 100.
Traditionally, we're controlling our speed with the throttle. The only time we would be proceeding at that speed is if we're trying to make up for past time. But the only real danger is, as you just mentioned, losing control and running into larger rock from the rover.
Yeah. Your air is about a foot and a half.
So status summary for the chassis. The chassis, of course, is already manufactured, hence the validation for us to want to reuse it. Its dimensions are shown. As you can see, this is just under the 2.2 square meter requirement that we need for the weighing plate, and our calculated weight for the chassis platform itself comes out to be 6.7 pounds. And now I'll have Gabe talk about the bolt and bearing failure for the Traversal.
Good morning, everybody. My name is Gabe, so I'm going to be talking about the bolt and bearing failure on chassis. So for our problem description, so all systems need to be able to connect to the chassis. This includes the vertical antenna on the rover, the science auger system, robotic system, and motor system. So I want to derive a process to find the optimal bolt or pin diameter that will avoid structural damage or deformation to the chassis. So for our design parameters, there are three major design parameters that I came up with. The first one is force being applied at the connecting points. Now this force being applied at the connecting points will create a shear stress onto the bolts, and there's a potential risk of shearing the bolt off. The second, continuing that, there's also going to be a bearing stress onto the plates. So the potential risk for this is causing a bearing failure, which is basically bolt deformation. Or in severe cases, if the force is great enough, it will cause a shear tear out, which is completely tearing out the chassis. So the second is bolt or pin material properties. So higher tensile strength usually equals to higher density. It's not always the case, but it's a good rule of thumb to go by. And then the third is the bolt or pin diameter. So the smaller the diameter equals the higher bearing stress on the plates being applied to it. So performance criteria. There are three major performance criteria that I came up with. The first is kind of obvious, but the bolt diameter cannot exceed the chassis tube dimensions. The second is bearing stress onto the plates cannot exceed the yield strength of the chassis material, which is aluminum 6061-6. And the third is density area ratio. So density area ratio is basically the material density times the area of the diameter, which is the minimum bolt diameter that we come up with, which is correlating to the materials. So for evidence of the baseline feasibility, these are the equations.
Safety factor on the bolt side?
What was
We
that?
have it at safety factor of 1. Is that what you're going with? For the bearing stress? And safety factor.
So for the safety factor, I'm my equations later down the line, we can input it as what we want, but I'm using a tube. So I'm using 2 because aircraft uses 1.2 to 1.5 and automobiles use 3, so I felt like 2 would be a good compromise since it is supposed to be quote unquote going to Mars. So these are the equations I used to derive an equation in the following slides. It's the single shear stress, double shear stress, bearing stress, safety factor, and then von Mises. So the von Mises is just a pure stress equation. So for the single shear, there's these equations that I came up with. The first one is going to be the minimum bolt diameter. So P equals to the applied force in pounds. F is going to be the applied safety factor. UTS is ultimate tensile strength of the material that we're going to be using. And X is going to be the amount of volts that's going to be into the system. These two bottom ones are going to be the bearing stress of the applied force. So A is going to be the plate thickness. D is going to be what we find in the first equation. X is the number of volts. So then we'll be comparing that to the yield strength of the parent material that it's going with. So this is the same equations, but this is just for a double shear scenario. As you can see, the bearing failure of BA changes to 2, or P over 2. That's because there's 2 plates. So I want to show you guys how it works. So I use the science auger system as an example, but the science auger system is only 20-pound force, so I want to exaggerate it and I change that to 650-pound force just to give variability to see how it works. For this one, I use a single bolt and with the factor of safety too. So we can see that I gave a list of materials of what we can access, MasterCard, other retail materials elsewhere. And I also included the tensile strength of those materials. Now, the yield strength isn't actually the yield strength of the material, it's the yield strength of the parent material of the chassis tube. That way you can see a side comparison of the bearing stress and the yield strength. And then as we can see, that the only one that works is aluminum 6C61-G6, which is it just barely works. So then we added 2 bolts to the system, and as we can see, the numbers changed quite drastically, where we have 2 viable options, which is aluminum 2024 and aluminum 775. And as we can see, the density area is also changed as well. Going back to the other slide, you can see that it's either 3.7 and 2.7. And for those values, it changes to 1.9 and 1.4. So for our status summary,
So how are we isolating these guys now on safety?
so we have we're using a factor safety of 2. And as you can see, for this set of data, we're using 2 bolts. And then we're using a pound force of 650 pounds to exaggerate.
Yes, but I guess I'm having a hard time putting on the table here. How do we identify aluminum 2024 and 7075 as viable options? What's the criteria that we're using to identify them as?
So that criteria is just the accessibility of the material.
So if we go back to the previous one, looking at this table, how can I point to specific rows and say, this design works, this works, these don't work.
Great, I should have included the red and green.
Yeah, but it's not looking at it which ones are, but if I look at this number from the very beginning, based on the requirements, how do I isolate which of these would be valid designs? There's no safety factor in here, so I don't know if we're meeting safety factor 2.
So we're inputting a safety factor 2 as a requirement.
So you're forcing it as a safety,
Correct. So we're not guessing what kind of safety factor it is. We can input whatever safety
so you're
factor.
computing the minimum bolt diameter for a safety factor 2.
Right.
Okay. I think the follow-up to that, for example, I don't think you'll find bolt diameters made in 0.17, but it's, you gotta look at what a size 10, size 8, what those are. So I think what you gotta do next, it kind of tells you the minimum size. Start looking at the bolt sizes for the given materials that work, whether they're like 1032s or what for 632, and then list them here, the actual off the market. So I'm assuming you have to make your own screw size from scratch, and then say what the corresponding safety factor is.
Right.
So this way you can then say, we're going to need this bolt of this size, or this bolt of that size, this bolt of this size. Then you can isolate, which ones work, which don't work. And then based on other criteria, you can select them. All these are strong enough. Maybe if you care about weight, see which of these are light enough.
Right.
So then you can pick which bolts are the best ones to work with. They're all strong enough. And if you care about minimizing weight, you can then compare the actual weight of the bolt. The same length, see which is the lighter one.
That's why I was trying to get the density area ratio. Because not all of our connecting systems are going to be dependent on bolt. It's also going to be some of our systems are pin.
But I think right now you're assuming that the pins would be made in these non-standard sizes, which they can, but you're going to be spending a lot of time on the lathe in the machine shop. It's best to look at what these sizes are and then pick a fastener off the shelf that's pre-made, that's following standard size, and then take those dimensions and then rerun this analysis, but the output of that would be your safety factor. So then what you have is for different material, what that pin size or bolt size needs to be, and what the corresponding safety factor is. It should be hovering around 2,
Right.
a little over 2, so that you're safe. And if you want, you can let it go a little bit under 2. That's your call.
Yeah.
But then you can identify how heavy are each of these sizes. So then you can pick the bolt that is strong enough and the lightest possible. Now you can argue you have the lightest possible bolt size.
Right.
I think you just got to take that extra step. I think this is great, don't get me wrong. But the way you're selecting aluminum 2024, 775, I think what you got to do is take that extra step and then look at standard sizes first. And you'll find all these are strong enough for their material. You can isolate by weight, which is the lightest one. And if you care about weight, that's what identify the strongest, well, this one that's strong enough and light as possible. Yeah, now you can argue you have the lightest possible bolt size. And that'll be a valid argument. Yeah, can't complain about that. You just take that extra step, and I think it'll be fine. So, because right now I just don't see how you can isolate those two from this information. The criteria for selecting the bolt size isn't clear to me. So I think what you have to do that extra step so you can isolate. Because in neither column, it's aluminum either the greatest or the smallest. It's somewhere in between. So I don't know what the upper and lower limit for making this decision is. I don't know what the sweet spot is. So if you have that, then it's easy to identify why this is the best. So if you do that.
This is test.
The antenna mass, our objective is to produce a structure capable of suspending our communications array. Our communications array is vital to our system. If there is any malfunction or failure with our communications array, we lose complete functionality. So it is absolutely essential. Some of the requirements that go along with the antenna mast are we need to be able to attach our PVC housed antenna as well as our 433 megahertz antenna. In addition to this, we need to also have a mounting position for our ubiquity device, which is then connected to our PVC housed antenna. And lastly, we also need to have the antenna mounted to the chassis system. Some of the design parameters that go along with the antenna mast. First is this geometry. We need to find the optimal cross-sectional area for the tubing in order for it to reduce the amount of jerk that the payload will experience as it sways. We also need to take into consideration the mass of the antenna components, which contribute to the jerk that will be experienced. And the second thing is the tubing material. We're planning on going with carbon fiber tubing because it has an excellent strength-weight ratio, which is what we're looking for. And we also need to relate the material strength to our stiffness K, which you'll see later how we model the antenna mast. So for the performance criteria, we want to aim for a design factor of 3. The reason we want to go with 3 is because, as I had said earlier, the antenna mast is vital to the system. If something were to happen or failure, we lose complete functionality. So we need to make sure there is very, very, very little room for failure. Another criteria is the height of the antenna mast. It needs to be somewhere around 1.5 meters or 59.1 inches. The reason that that we need to correlate with these numbers is our control team has given us positive feedback as to these values for essential excellent communication with the base station and with the control team. We also want to have a target weight of the mast be under 2 pounds. So for our evidence of baseline feasibility, this is essentially how we're modeling the antenna mast. As you can see, we modeled it as a spring mast system with essentially the rover being M1, as you can see, and the mass, and the mass of the components in the antenna as mass 2. And as you can see, K is representative of the stiffness of the rod material. As you can see by the picture, it is exaggerated as far as the bend itself. But as you can see, if there is a impulse force or an impact force exerted onto the rover due to some displacement, there will be a resulting displacement from or to the antenna mast itself, which is essentially providing a jerk force. And that jerk force will then determine what kind of stress concentration that we have on the antenna mast, which will allow us to determine an optimal or a preferable design factor. As you can see here for our spring mast model, these are our governing equations of motion. They correlate directly with the displacement of the rover itself, as well as the mass of the rover. And we also implemented the formula for an impulse transfer or an impact due to the change in velocity of the rover, which in this case would be our maximum velocity, as we want to take into consideration the worst case scenario as our primary evaluation. And this governing equation for motion also relates back to the stiffness K, which we can relate to the choice of material for the mast itself. From this, we can then determine the stress concentration as followed by the formula that is given. And what we would be able to do is, since we need to calculate the moment of inertia that is exhibited due to this stress concentration, we will be able to choose an optimal inner and outer diameter of this tubing that will be sufficient to reduce the amount of jerk force that is induced on the system.
Question, so this tubing, are we anticipating purchasing it off the shelf?
Yes.
So I think it'd be good to look at what sizes exist already. Maybe, and I don't know if it's a function of wall thickness for a given outer diameter, like a lot of steel tubing is, or what kind of flexibility you have. Because then what they could do instead is identify what tube sizes exist and use those as inputs to see which of those satisfy your requirement. Yeah, you kind of do it instead of kind of find it, maybe look at if you're going to purchase it off the shelf, unless you're going to custom order it, which would be more expensive. Look at what's available and which of those off the shelf satisfy your requirements and see what the output safety factor is. So say what your safety, if you have safety factor 3, see what they are, and then so guys, by be able to see which of those will give you the lightest one. Basically, which of those, just find what that surface area is, and you see what the lightest one will be. So you can write that moment of failure transmission outer diameter minus the thickness for R1. R2 outer diameter, and R1 make it R2 minus T thickness. Because typically they tell you outer diameter and wall thickness. It's easy to measure. Measure the outside and measure the wall, and that's typically the parameter you give. So if you have that as inputs, then you can isolate which combination satisfies the requirements, given that the number of outer diameters and wall thicknesses are specified by the tester. So once you have that, you can say, I need this tube and this tube. That's the way to, when you're generating, so you're still generating the code for it, start with that as inputs. Like, vary your R based on the stock size. Vary the thickness based on the stock size. So that's where you can directly isolate which of the work, and then look at after that weight, so that you can meet your 2-pound weight requirement. So you have the requirements, so when you output it, have those, so you can isolate which of the ones that work.
Thank you. So as you can see for our remaining analysis, we still want to generate a MATLAB code and a Simulink plot to basically evaluate our results and the response that we anticipate on seeing from the jerk force exerted onto the antenna system. We also need to conduct material testing on the material selection for the rod itself, and we get to produce a prototype model until this analysis is complete.
Hello everybody, my name is Maurice Castillo and I am District Robotics Lead. So today we'll be covering the robotic system. I'll start with the robotic overview. Our robotic arm consists of mainly 5 joints. Our robotic arm is powered by 4 stepper motors and 2 linear actuators. We have 1 stepper motor here, J1, allowing us to rotate the arm. We have another stepper motor here at J3, which helps us to essentially rotate the arm, at least this portion of the arm here in the YZ plane. And then we have 2 other stepper motors at our gripper here in order to allow us to rotate the gripper infinitely many times and also close and open our end fenders. And then we have our 2 linear actuators, our lower actuator here and our upper actuator here, which allow us to essentially lower the arm and extend it forward. So our robotic arm has to complete a variety, or rather participate in a variety of tasks. It has to lift payloads, rotate knobs, open and close doors, type on keyboards. So it needs to be very capable. And part of our robotic arm this year, we have placed a goal upon ourselves to have a target goal of 30 pounds. However, our objective is to weigh less than 34 pounds, which is the current weight of the arm. And throughout our arm, there will be factor safeties around 1.5 to 5. Each component will vary depending upon what it will be used for.
Why do you have factors of safety up to 5?
It's just number 1, mostly structural components.
Why so high? If you're going off the worst case scenario, you're assuming that's going to happen 5 times greater. I mean, it just seems. Or is it what's the safety factor based off of?
It's based off the yield.
But exactly, why so high for the yield? If it's based off life cycles, I get it. But when it's not, like this is really high. Like this is rather high for the yield strength.
And it would also depend on the load
All of that leads to the stresses, but remember, we're comparing to the yield strength. Worst case scenario, absolutely worst case scenario. But it's just really high. Or just purely arguing on the yield strength. Safety factors are high when we're looking at fatigue level. Because, but then you specify how many cycles. 5, it seems absurdly high for a yield strength. Because that's going to make your arm heavy. It allows your arm to be heavy. Almost at least 3 times heavier. If you go up to like 1.2 or 2, it's at least twice as heavy. It'll allow for that. That'd be the long-term effect. If you do everything to 2 or everything to 5, you can be at least 2.5 times heavier when you don't need to do. So I would reevaluate that number.
Okay.
For maybe some parts just can't be as small as you need, but for the most part, you seem too high. Second, you mentioned that the arm has to have a certain level of dexterity,
Yes.
such as being able to lift payload. So how much weight do we expect this arm to carry?
The arm should be able to lift a maximum of 15 pounds.
22 pounds?
15.
15 pounds? And what about in terms of range of motion for the
Range of motion of the arm.
hitting knobs and things like that?
As for range of motion, the arm should be able to reach 5 feet above the ground, and has a maximum horizontal span length of 55 inches.
How accurate do we have to be when you type on a keyboard? How big are these keyboards? Are they like this big or are they really small?
They normally just use standard size keyboard, and for that reason, we use stepper motors to give us accuracy and precision.
So how accurate? So if you're looking at an arm, a small half a degree from the motor can translate into half an inch to an inch, which you instead of trying to hit like the S key on something else on your keyboard. But ultimately, what's our tolerance? How when we want to hit a key, how close or how far can we be off from the center of that key? What's our range of motion? How accurate does that need to be? Does that have to be exactly like 1 inch, 1.0001, or like 1 1/4 acceptable? Like how accurate does our kinematics have to be in our design of the arm? I think that would be part of the performance, given that you described the description. You have to hit keys, open and close doors, but really, flipping switches and the keys are kind of the big ones. What if you hit the wrong switch, like open, the vent system? So this hypothetically, like how far or how much air in your motion are you allowed? Tolerance.
Well, I'll just say that.
Yeah. Do you have one in mind?
No.
That needs to be. If you want to hit those 2 bullet points on there, you need to design your connects to that, and your motor selection, your control, your arm has to give that amount of accuracy. So that needs to be.
Hi, my name is Michael. I'm familiar with the truss structure. As you can see, this is our robotic arm. I'm redesigning from purple selection right here, excluding the linear actuator. It's going to be just the truss itself. Always going to be able to support the payload and the dripper assembly along with the motor assembly without yielding. And
Go back 2 slides.
without yielding, and to decrease the weight from the gripper because of the right angle of your box weight. Overall, we're trying to minimize weight for our whole system, as well as keep the community. Some of our design parameters are going to be the material. Yes, it's actually going to be in the high performance material. We're targeting for 2 pounds. And one of the things that I can change is going to be the geometry of the truss itself. And this is going to be a 2-truss system. For our performance criteria, we're going to have a target weight of less than 2 pounds, give or take, depending on everybody else's system.
So based on how you specify the criteria, let's say you shave 3 pounds off of the arm. Is that a bad design?
It's a bad design. 3 pounds off, the 6 pounds.
Are you going for a total weight of less than 2 pounds, or are you
Just for the truss itself.
well, the truss itself has to be less than 2 pounds?
Yes,
Okay.
that's what we're targeting.
I see. All right.
The safety factor based off aluminum, which was one of the inputs that we chose. Ignore the typo. There's a presentation here. This is supposed to be a Dropbox. It's supposed to be range from safety factor greater than 1.5 with the weight of the goal of weight reduction in mind, and we're supposed to be understanding truss must not fail, because it's a major source of complaints. I've modeled the truss as a simply supported beam or an overhanging beam. The point load at the end as the assembly of the gripper and the payload. I also use a distributed load from the weight of the beam, possibly to incorporate the weight of the motors and the belt pulley system. The length of B is going to be where the linear actuator is going to be positioned underneath the truss as one of these supports. My governing equations are going to be bending stress, because the truss is going to be pushed up by the linear actuator and then pulled down by the payload and the gripper assembly. And from that, I'm determining the safety factor. I approached the problem for the Bernoulli beam equation, finding the shear stress and then integrating it to find the moment equation. Because it's a simply supported beam, the deflections at the support are going to be 0. And then based off my input of geometry, I can change the moment of inertia, because I'm going to be doing cutouts for the truss. And my max deflection for a overhanging beam with a point load on the end is equal to that.
If you go back,
Yes.
so you have, if you're looking for a moment, which is a second order differential equation, you have one boundary condition. What's your second boundary condition?
Since there's two supports, there's going to be two boundary conditions at Y and A.
Well, what are they?
It's going to be at 0 and 5 inches. It's going to be at this support and this support.
So both of those are set to 0.
For deflections.
Okay.
And here are my shear and moment diagrams based off the equations I got. We're finding that the force is greatest at the linear actuator support. And these are some sample calculations based off a solid aluminum that I ran through ANSYS, and it correlated with my hand calculations. So that way I was able to run somewhat correctly for ANSYS.
What is E6? Why don't you just delete it and put an M in front of E so you have megapascal?
Yeah. That's how ANSYS outputted numbers.
Oh,
So
you-
I was comparing it with ANSYS.
No, I'm not. I'm not arguing with the number itself. I'm arguing with the way you're representing the number. So E6 is for a computer, but you can show 10 to the 6, or you can take advantage of the metric system, drop the E6, put an M in front of P, and call it megapascal, just like you did with the yield strength. So you can have 276 megapascals over 5.20 whatever megapascals. Makes it look a lot easier to compare. Because I don't know, is that a typo? Is that an exponential times 6? I mean, intuitively, I can suspect that that's 10 to the 6. But for the novice reader or the businessman who's going to look at that, like, what is that E? So just make it megapascal. That's the beauty of the metric system. Put an M, make sure it's a capital M. It's not a micropascal. But if we go back, so what are these from? The calculations that came up with? Okay, so what is this? So you said the next slide gives you numbers from ANSYS simulation.
No, these numbers I compared with ANSYS simulation for a solid
Gotcha.
aluminum beam.
Right, but so these are from the previous slide. If you
Yes.
take this final moment, now where does that moment happen? What point? Because right
The
now,
moment's going to be corresponding right here, which is going to be the max, where it was
Okay, so at that point, that's where you're finding the stress.
Yeah.
What you could do, take that moment curve and have a stress curve plot. That's the stress plot. Because then, ultimately, what you care about is the stress. Change the moment of inertia is another area. You could have a uniform moment of inertia, which is standard, but this way you can see at least where the stress is. Remember, what you define as your criteria is safety factor. Above that, forget stress. You can actually compute the stress, normalize it by the strength of the material, and have safety factor. So you can have a clear indication that either A, you're failing, or B, you're passing your requirements. And if you are, by how much? So if you go back to your next slide, right now our safety factor is 53.8.
For a solid aluminum beam that I use for simple modeling to verify the data.
I would imagine that'd be
It's solid aluminum, and then there's a really low point load at the end, and it has a 3-inch height.
I mean, all that's going to do though is change your moment of inertia. You still have the same bending scenario. I think again, you guys talk about weight. You got to factor that into this conversation, and that's going to manifest in how you calculate moment of inertia. A different beam. The next slide, right? So if you go to the previous slide, right here, all of this is independent of beam shape. Doesn't matter what it is. Following slide, the second bullet point, all of this depends on beam design. Your maximum deflection, all this. I think going back to my earlier comment about tolerances, that's going to tell you what your Y max needs to be. So you can, that depends on moment of inertia. And then having a weight requirement, you're looking at going down to 2 pounds. With a safety factor of 54, I mean, you're overkilling it. I don't know how much it weighs though, so I can't say this is a good design or not. It looks like it's really strong, but I would argue maybe heavier than 2 pounds, and you have a lot of room to shape it down.
Yes.
So to know if this is a good design, I mean, every output has to compare to your requirements, and you said 2 pounds, so you can basically take this information and see how much 2 pounds is.
So pretty much with the solid aluminum truss, it was 0.7 kilograms, or 0.7 pounds, and that's just for one. And using ANSYS, I was able to calculate it numerically. It was a little bit difficult to calculate numerically by hand.
Why?
Because of the
cutouts.
cutouts.
Make your life easy. Go back to the first slide where you have the truss. Right here. All right. Let's look at this truss. Where are the most critical loads happening in bending?
Based off that diagram,
All right, but let's isolate that. So that's the axial position. What about the transverse position, vertical position? Where do we care most about bending?
right above it.
Right above it and right below it. Compression and tension, those are the 2 most critical points. So let's make the assumption that the top 2 ends, we're going to size up to take all of the bending. And I'm going to double it. So essentially what I have is 4 faces that, if I take a cross-sectional slice, I have 4 squares, 4 rectangular faces, wall thickness, of height, and those 4 are going to make up the moment of inertia that's going to take the entire bending load. So I forget the cutouts. The truss system is there just to distribute the force, but I'm going to design this so that mine can take that bending moment. Simple as that. You don't worry about the trusses. They're not taking the bending.
So there's longer shape.
Don't do it that way. You got to simplify it so you get something that works. And you do it by identifying where's the worst case happening and assume that those are taking all the load. Yes, I'm going to slightly oversize it, but that's, you have room to play with. That's what the safety factor is for. take the top and the bottom, treat them as two straight columns, project that a few distance away, and you basically look at it from a cross-sectional view and see what the moment of inertia of that is. Make it a function of the wall thickness, the height, and there's how far they're spaced out. Unless either of those are constrained. Now you have a moment of inertia. Change in diameter, you can control all of that. And so, and then once you have a certain size, you cat it up, and then you put it into ANSYS and see how close you got. You'd be surprised how good you can get. They designed wing boxes by hand back in the day. Doing the same approach, so don't tell me we can't do this now.
Based off my ANSYS results with the truss that we redesigned, it gave me a really high safety factor in the low weight, with a 40% reduction in weight.
So
based off
which
of
were the
that.
ANSYS results?
ANSYS,
Go back. Where are they in any of these slides?
it's not on these slides.
Then you can't make this argument based on the evidence that's presented. So you have to have the numbers to support the statement. There's no answer here. So based off these, we can take it off these, yes. You go off this, yeah, right. But if we're talking now about ANSYS, what was the, let's say, what were your boundary conditions that same problem? How did you model that?
I modeled it as a pin support at this location, and a pin support at this location.
Okay.
And then I put that in graphene affecting the based off these results, it does predict a high safety factor. Testing has to be done to validate results after we prototype.
So do you know like what the wall thickness is, or what is the...
I chose an 1/8 inch, or an 1/8 inch and 3/16 inch as some of my inputs based off the geometry.
How tall is this? So you gotta get these good geometric parameters so that we can see where you can shave room off of. Can you summarize this? Like this is so far oversized, and this is sort of the geometry that we're looking at. But I think you can simplify that beam, assuming that these 4 points are taking all the loads. Because what those trusses are, what they do is they're what we call shear walls. They just sort of transmit the loads amongst the beam. But we assume, based on how bending works, that the extremities are taking most of the bending. That's why an I-beam looks the way it does. It has more material on the side, on top and the bottom. That's where the biggest stresses are. And they assume that that takes all the load. And the thin wall acts like a shear wall to distribute the shear between them, so that they're not two separate bodies, but one rigid body. And that's how you can approximate this. Even if you got it through the middle, don't worry about it. That's when you're assuming it doesn't take any of the bending. If it does, all it does is alleviate the stress of the bending. So it makes it a lot easier.
So I helped the robotics team with choosing out the motors, belts, and shaft. So here's some pictures for you guys to see what I'm doing. The top picture is pretty much the motor assembly from last year. I have some motors into gearbox. And the second picture is more the stress structure. Just look at the motors, the gearbox, and the pulley system itself. So for my problem descriptions, I need to make sure that the motors will provide enough torque at J4 that will lift, be able to lift a payload of maximum 15. And it should weight in last year motor assembly. And I gotta make from there the requirements, like make sure the belts and pulleys gotta mesh correctly. And make sure that the shaft, the driven shaft, that can withstand the force generated by the belt tension, loads, and holding torque from the motor. For design parameters, so for torque is boiled down to the gear reduction in the gearbox and pulleys. And weights, I would have to choose different motors, gearbox, and pulleys that will give me the required weights. For belts to mesh properly with pulleys, I will have to choose a different set of pulleys that will give me a 2-to-1 gear ratio, because different pulleys will give me different pitch diameters and it will affect the mesh. And gotta make sure the belt's length gotta be correct and proper tensions in the belt. And for shaft, I want to keep the same diameters in the shaft, so I'm gonna be looking at changing the material of the shaft. For criteria, so for torque, I want to have a required torque of 49 pounds-inch with a service safety above 2. And then it should weight, the motor assembly should weight then less than 2.92 pounds. And for belts and pulleys to mesh correctly, I need to have a minimum of engaged teeth on the small pulleys equal to 6. And I want to keep the center distance from the pulleys to the motor, from the driven shaft to the motor, 12 inches. And for belts tension, I want to have the required tension with 3.5 pounds force, not pounds mass. For the shaft, I want to have a safety factor above 2. So now I'm going to show you guys how I calculate the 249 pounds-inch at J4. So pretty much the J4 is rotating, and this is assuming the worst case scenario when the gripper's assembly is flat out. So we have the gripper assembly mass with the max payload, simple free body diagrams with a torque equal to distant temp floors. I got 249 pounds-inch. And from there, now I know the minimum required torque. I'm going to choose motors, gearbox, pulleys that will give me this minimum required torque with a service safety of above 2, and it must weigh that less than 2.92 pounds. So as of now, I'm looking at a NEMA 17 into a 100-to-1 gearbox to a 2-to-1 pulleys. This will provide a 775 pounds-inch. Keep in mind this is with a service safety of 3. Keep in mind this is the holding torque. So operating torque will be a bit lower. So it will bring down my service safety to like around 2. Because holding torque usually is the max, so that's why I'm looking at the holding torque only. And this assembly, I got a weight of around 1.5 pounds. And then the next prompt. What?
Really light for how much torque it's got.
Yeah. The motor assembly itself is like 1.2 pounds. I think. It's the specs, just the specs I got online. I can show you the specs. And this is a holding torque only, but operating torque is around like 400 pounds.
It's about 80 foot-pounds.
60.
Yeah, that's 60.
I can lower it. Just choosing.
Those numbers seem high
Yeah.
for how I like that.
Yeah. So that's why I'm trying to buy the motors.
Notice it really powerful. I'm assuming they're moving really slow.
Yeah, it's super slow. So the operating torque is 2 RPM for around 24 Newton per meter. So it's pretty slow. If you go higher speed, the torque will decrease.
Yeah.
Yeah. But I make sure it doesn't go below 1. Okay, so for the next problem is the belts and the pulleys that I mesh correctly. So the first thing, I have like 3 different aspects that I have to look at. The first one is the pitch, the width, and the type of belts. So now I'm looking at the type XL. Width is 3 1/8, and then pitch is 0.2 inch. And numbers of engaged teeth, I gotta make sure the required minimum of engaged teeth on the small pulleys gotta be at least 6. So then from there, I'm going to choose the set of pulleys that will satisfy this number, and then I'll calculate the required belt length from the set of chosen pulleys. So this kind of pictures for you guys can see that how I get. I have 3 governing equations. The first one is ZM, is just calculating the number of numbers set of pulleys. But from here you can see that the set 12 to 24 teeth is pretty close to the minimum line, and the 14 to 28 teeth will be pretty much above the line. So I gotta make sure the weights will take into account this. You choose the smaller set of pulleys will give me the lighter weights.
That doesn't give us 5.
Yeah, I'll talk about that in a bit. Because if you add a tensioner, it will decrease the angle of contact and it will increase the number of engaged teeth.
But the weight of that tensioner offset the weight of the 14.8. So the 14.8 is a bigger one. Was adding a tensioner,
Yeah, I'll say this.
how did that combined weight of that plus the tensioner
Yeah.
compare to the one of just 14.8?
Yeah, I haven't looked into a cap tensioner when I add yet, so
From that, just to keep the purpose.
So, and then the third aspect is proper tension in belts. Actually, I looked through 4 methods on, because my initial idea is to figure out the theoretical required tension in belts, and then from there I'm going to use a tool to measure what the tension is. But the first 3 methods gave me like really big numbers, like 300, 400 pounds force, and which is exceed the maximum for tension the belt can take, which is only 141 pounds force. So I went with this method called the tension and deflection method, which you have to calculate or measure the deflection force in belts using a belt tension gauge, a tool right there, and adjust the tensioner until you meet this recommended deflection force. And I have a table of recommended deflection force right there, which is around 3.5 pounds. So here's a method on how you can use the tension gauge. Basically, you have 2 O-rings. The one on the bottoms has the deflection distance per span. You can adjust that, and then the small O-rings will tell you the deflection force. Question?
Yeah, I got a question. Just about your belt length. So it sounds like you guys kind of want to go with like a 27.6 inch belt.
Yeah, it's standard. It's be like 27.
Okay, so that was my question.
Yeah.
What the standard belt length was.
Yeah, pretty close to the standard, but I'm pretty sure I'll need to go over that a little bit because I'll add a tensioner though. I'll provide the tension. And then from the deflection force, I can use the governing equation right here to figure out tension in belt, which is around 3.5 pounds force. And then from there, I'll do my analysis on the driven shaft on a discontinuous in diameter shaft. Now you have from this you can see the shaft will be supported by 2 bearings, bearing 1 and bearing 2. The loads from the payload and grippers, and the pulleys will be at the right end, which will have a force radio from the tension, the holding torque, and no tension or compression. That's why the 4-axle is put at 0. And then from the pictures, I will have to do sum of forces, sum of moments, and plot that in the shear versus moment diagrams to figure out where is the maximum bending load is. And then I've got the maximum bending load of 7.28 pounds at bearing 2, where the shoulder fillet is. And then since I have a shoulder fillet right there, I have to figure out the KF, which is the chest concentration. And then chest concentration factor is just Q, which is notch sensitivity, and chest concentration factor, KT, from the graph. You can find them both. And figured out, plotted in KF, and plugged in the governing equation of to find the chest max. And torque, the holding torque earlier is the max torque that I'll be having. So it's 775 pounds-inch. Plug that in. Plug it in the safety factor, which is just the yield strength over the truss max. And here's the plot of the range of yield strength for that give me the output of safety factor. And I plot some of the material so we can compare. And we can see that aluminum is below 1.5, steel above 2, titanium's plate above around 3. So my question for a status summary. Right, as of now, I'm thinking of using NEMA 17 to 100-1 to 221, but this can change if we need more or less torque. For pulleys, I'm going to go with a 12 to 24 set, like I said earlier. I will have a tensioner that will adjust the angle of contact, the engaged angle, and this will increase the number of number of a small pulley. And for the driven shaft, I'm thinking of titanium because it's above 2, even though some steel is above 2, give me a safety factor above 2, but titanium is a lot lighter than steel, so that's why I'm trying to go with titanium. And I need to do more study on the shaft for the key channels, that's what I'm doing right now, because we'll have some sets through, and I want to do analysis on if the key channels will affect that. And an effective way to add tensioner, from there I can compare the weights and see which one will be better if I go with a lot bigger set of pulleys or just a smaller set of pulleys with a tensioner. Well, either way, I still have to add a tensioner, so I think I'm going to go with a smaller set of pulleys. And then a prototype. So, any question?
Can we go back to your free body diagram?
On the shaft?
Yeah. First one, what's the, so you're assuming no axle force, right?
Yeah, because tension.
Now, where you have the torque method, that's basically the holding torque being canceled out by the motor. You don't have a reacting torque in the opposite direction. But in addition to that, is the radial force that you have there, is that representing the tension of the pulley, the tension of the pulling on the pulley, and inducing a bending moment on the shaft?
Yeah. I'm assuming the belts will have a tension on the top and bottoms.
Yeah.
And then
They will. It wasn't intentional.
yeah.
But you could imagine from the shop output, you can interpret that almost as a cantilever. You have the torque output, you need the reacting force, by the way. But you have the torque, holding torque, that's one. That's a torsional load. But given that this is an output shaft that's not supported, or is it supported on the output?
Not supported.
It's not supported. So it's also going to, that tension is also going to induce a bending moment on the shaft.
Right.
With or without torque. So you have a combination of torsion and bending. So going back to the next slide, is N max, what is,
It's the max bending moment.
so is that what N max is accounting for? Is that where's, that's at the 9, so that's the bending moment from the radius?
Yeah, because I did shear versus plot the shear and moments diagrams. Yeah, so I figured out the max bending moments that the bearing is not at the band. But because like you said, it's bending, then it's going to bend at that bearing too. Yeah, because the pulley is pulling it.
So check at the bearing and also where the transition happens.
Yeah.
There's 2 stages. It varies axially. The moment varies axially. So the moment will be higher at the output, but where you have that fillet in the shaft, they have a stress concentration there. So even though it may be the same moment, the stress would be amplified. One, because you have a smaller moment of inertia. And then 2, you have stress concentration there.
So you cannot just do the KF factor in like that, or you have to do
But you can. All right, so let's go back to the previous slide. So when you computed your stress,
right.
what diameter did you use for your moment of inertia?
Do that stress.
What diameter did you use?
The bigger side will be 0.375, and the small one is 1/4 inch.
So which of those diameters did you use for a moment of inertia?
Small.
So okay, so you use the small one and and you assume the bending moment at the output shaft?
Bending moment. Yeah.
All right, so the worst case scenario. All right, that's
Yeah.
fine. Just making sure.
Any other questions?
Moving on with the base plate. So we're choosing a base plate to be made out of a carbon fiber composite with an aluminum core. Doing this will provide a high moment of inertia without much of a weight penalty. The purpose needs to securely mount the robotic arm to the chassis of the rover, and it needs to withstand both the dynamic and moment forces induced by the robotic arm during worst case scenarios, 2 of which I will show in the slides. So for design parameters, we have the dimensions of the base plate itself. Length and width actually more or less will be the same with any changes actually happening on the shorter edge. Thickness will be the number of plies plus the core thickness of the aluminum core that we have. We're going to start with 1/2 inch, but move between 1/2 inch and 1 inch through our testing. That will help us find, through a 3-point bend test, the modulus of elasticity. Other variables that can change would be the center of mass of where the robotic arm is, depending if it's fully extended, if we're picking up our payload, if it's pulled back upright. So R1 you see is just the radius along the lateral direction from the center of mass to the point of rotation of the robotic arm, and then R2 is the vertical height of where that center of mass is. And the Poisson's ratio is something that also will need to be found. That goes into account for the rigidity, which I'll show in the next slide. But that will be determined from the composite dimensions, actually, as well. The max dynamic force, depending on our loading scenario, can come from either a drop or when the competition specifies a 1 meter drop. I'm thinking it goes down kind of like a ramp, so like a slope, and then it just stops on the dime if it were to hit a rock. So that force I'll go over as well.
So could you say that that's a parameter that you control?
Well,
Or is more or less a requirement that we have?
for the force, if it's going down a ramp, it's more going to change because of just the angle.
Yeah, no, I'm not, what I'm asking is that a parameter, or is it something that we have to meet?
Not for
Yeah, I wouldn't treat that as a parameter. That's, you have to find it, that's a scenario we have to satisfy. It's a requirement you have to meet.
Okay.
So you should list it as a requirement, not as a parameter.
Alright.
We don't control that, we just try to meet it, survive any scenario.
Yeah, so then the last two would be then just scenarios that could happen as well, not really parameters that we can change. But
Yeah,
would enter
all of those, like, those just really can play into your requirements that you have to satisfy.
Got it.
This will be like what you check in comparison to.
Yeah. For the performance criteria, since we want to assess if it is indeed safe to put the robotic arm onto this new baseplate design, we're aiming for a design factor greater than 2. And we're assessing this through the deflection. So we're going to find analytically what the deflection anticipated can be in these different loading scenarios and comparing that with the deflection that happens at the yield point when we do a 3-point bend test on a carbon fiber composite with the aluminum core. And our goal is to have it weigh less than 1.5 pounds. That would be a little over a pound less than what we had in my previous baseplate design made out of aluminum, which was around 2.5 pounds. And this is kind of a brief overview of our baseline feasibility, what we're going to have to do to assess if the deflection anticipated is indeed good enough for the maximum deflection that our composite could take. First things we would have to do are to do 2 different kinds of tests to find the Poisson's ratio and the modulus of rigidity. That can help us determine the equivalent stiffness of the base plate, which would be relevant in one of our loading scenarios. If those parameters do meet our design factor, then those are the parameters we would keep. Otherwise, we would reiterate to go more likely with just a thicker core. So we're just starting at 0.5 inches for a core. And if it doesn't meet our next iteration, we'll just be thickening the core to have a higher moment of inertia and therefore greater rigidity. One of the loading scenarios is something that we talked over, just straight down drop onto the rover. So I modeled the equivalent stiffness of the system, taking into account the shocks and the tires, while also the rigidity of the base plate itself. That rigidity of the base plate is denoted by D, which is the equation of the modulus times the thickness cubed over 12 minus the Poisson's ratio squared. That number can be found in, was derived from Timoshenko's shells and theories. So our base plate can't be treated as an axial number. It is simply supported on all sides and is a rectangle. So when we're talking about force, it's just acting directly over top it. It's like a diaphragm stress. And moment force induced by the arm is Trinian loading that we would have to assess as well because it's a rectangular base plate. And then the alpha number you see there is a coefficient, which is going to help us find our deflection from just a vertical load, whether it be static or dynamic. That's pushing down on the base plate. That's derived from just the ratio of the lengths or the dimensions, length and width of the base plate itself. Moment load, we have anticipated moment load of what the arm is going to induce if it was picking up a payload and it is fully extended, what that moment will do. Putting it into the deflection that is caused from the moment, since to find that max deflection I talked about, since deflection acts linearly to the load that is induced on it, you can superimpose those together to find a equivalent deflection. Finding the deflection for M on a rectangular base plate though, as I'll go over in the next slide, will most likely have to be found computationally, which I'm working now in ANSYS ACP to make an equivalent composite and test that, since so far in Borg's formulas and the Timoshenko hand guide, there's not really equivalent deflection that can be found from a moment induced by a deflection caused from a moment on a rectangular base plate after this. More likely load. Okay.
Move back to the previous slide. How long is the robotic arm to base the gripper? 5 feet?
I think Mario mentioned 55.
Yeah, first base versus base to gripper.
55 inches around.
It's under 5 feet. So you're taking a 104 foot-pounds from picking up an 11 pound. I would imagine that's about 55 foot-pounds. Well, we're about double. Where's the extra? Just on that force. So if we're picking something up and it's like further just like that, it's literally the force perpendicular to the arm. So it'd be like 55 inches to 11.
And the weight of the arm itself.
Oh, I see.
Because this is a moment taken from up.
How much is the arm weight?
30 pounds.
Yeah.
34 pounds.
Okay.
And then I use those numbers from the 34 pounds, kind of like worst case scenario again, but we're most likely going to be able to get it through our designs to 3 pounds.
Okay. Okay.
Next loading scenario is what I talked about, kind of going down the slope, like if we just had a steep drop during competition and then we just stopped on a dime. The stiffness of the tires is going to help cushion a force impact that is going to cause a moment on the arm, as well as just the arm is going to create a static load on the base plate itself. Moment here, so the force that would be acting where you could see FD right here. If it was going to be a 1 meter high ramp, that force would be 788 foot-pounds. To find the moment that the arm would cause while the rover stops, it's going to be 1,538 foot-pounds. Finding that, I just ran a MATLAB script with just 2 for loops to find where the center of mass would be at the worst case scenario, holding that payload as well, since being straight out actually wouldn't be the worst case, because if it's vertical too, and then the rover just stopped, it would want to carry forward. So finding where that center of mass is to find what that max moment would be was about 1,500 foot-pounds. And again, we would have to take that moment and put that into ANSYS ACP to find a deflection that's causing the moment onto the base plate. Then we could throw the static deflection as well to find what that max deflection would be. Yeah, so it's just that. Some of these things that we can iterate and change most likely going to be the thickness. The short length could still change as well. The actual longest length most likely will be the same, just because it needs to fit onto the chassis of the rover. We need to find the modulus elasticity and Poisson's ratio still from 3-point bend test and also axial tensile test that we can use the Inshun machines for. To start doing those, we plan on compiling materials really soon so that we can get testing and analytics done within this month, and assess through analytics to see if that deflection is indeed that we anticipate less than by factor 2 the max deflection that a composite relay can take. Otherwise, we'll reiterate and increase the core thickness size.
Alright, my name is David, so I'll be focusing on robotic arm joints. So the problem description that we want the robotic arm to function and have it ready for the competition to perform their task. And by doing so, we want to find the torque required to discern the motors and actuators for the arm to operate by allowing the joints to rotate. For design parameters, we'll focus on stepper motors and linear actuators. The stepper motors, they provide the output torque to allow the joints of the arm to experience rotational force and to allow more torque to be added on those joints. That some of it has to reduce the RPM by attaching gear boxes to multiply the value of the torque to allow the joints to rotate more. And for the linear actuators, we'll be providing stroke, which is the length in which the actuators in motion will provide. And this is a very important metric that allows the force from that load to allow the arm to like push and pull and allowing the arm to move linearly.
Do you care about how much force these actuators can provide?
Under current setup, our most powerful linear actuators can provide 2,500 joules.
Why are they so good? Do we need 2,000?
For that reason, that's why we're looking over.
So what would be like, wouldn't that be a requirement now? So they're clearly too big and don't set the threshold too low because then they've got the you can move the arm. So part of those linear actions, not just stroke length, but force output. So right now, if it's too big, go with a smaller one, the output is even smaller as well. That's supposed to be a parameter that comes from that you should look into, or some type of variable. Because different actuators will have different stroke length, different strength.
So for our performance criteria, that our stepper motors and linear actuators both have a surface factor of 1.5 to 2, and this number is to ensure that the power of the motors is given enough beyond its capability without like changing the form of the robotic arm. With the output torque that's provided for stepper motors, and the actuators must fulfill the torque requirements that will be shown in evidence based on feasibility to enable the rotation of the joints. And the linear actuators must help maintain at least 55 inches, and this is important because by changing the arm length, it can manipulate the torque requirements that's needed in the joints. Thus, that can really affect the specs of what stepper motors and linear actuators we want to select to operate the arm.
Do you care at all when selecting different types of motors or actuators what the minimum excitation voltage is going to be, or what the current draw needs to be?
Yes, our linear actuators, they work on 24 volts, whereas all of our stepper motors work on 12 volts.
So if you have linear actuators that work on 12 volts, you could keep the same power supply, or having two separate power supplies, or have to have multiple supplies in your power supply?
As of right now, that has a big impact on the electrical system.
So why not have it a requirement that your linear actuator should have a 12 volt excitation voltage so that you can simplify the electrical system and make their lives easier?
Actually, it's more simplistic to maintain at least the actual 24 because of the fact that our power bank is 24 volts across. The linear
And
actuator.
make the stepper mode and everything else go to 24 volts. Whatever makes the system easier, just stick to that. Why have several different voltages? Or select your parts so that they all meet this one voltage requirement. So that you have separate, you don't have to have multiple power supplies or have voltage dividers. Just have one excitation voltage, one power bank, and you know what the current draw is going to have to be. Easier that way. Just specify that, have stepper mode, everything be 24 volts. Make sure that's a lot easier.
And then for evidence-based applied feasibility, we're looking at the robotic arm in an XYZ axis.
Dynamics, machine design, stress analysis, everything that has mechanical and it typically has that. Why do we have a 3D axis? Why don't you have X, Y? Why do we have to have Z in here? Because if you do, I better see a three-dimensional problem. are there any loads coming out? It's easier to represent it as XY plane, ZX plane, or I don't know, YZ plane. It's easier to see stuff in planes versus isotropic view for analysis purposes. And is that your origin right there? For that purple boxes?
That's just a reference, how we're looking at it.
Why not put it at basic J1 if that's going to take your moment about? Why have to translate that into that point? Very principle.
So for the governing equation for the torque at J2 would be considering the weights and the distance towards it. And the way joint 2 is going to behave is that it's taking the torque, the weight of the payload and the distance towards it, the weight of J5, J4, and J3, and then moving toward at the moment of J2. And as a result, we do get the torque J2 is 1,646 pound-inch. And this is to ensure that, like, while the arm does rotate, assuming around J2, that it has to like take account of like all the weights because it's rotating like all those masses. And then this, likewise, this was also good. J3 will also take the weight of the load, weight of J5, weight of J4, and then it's going to be rotating at joint 3, and the result would be around 775 pound-inch. And again, this would be the case for J4, where it's taking the weight of the 50-pound payload and the weight of J5 strippers, and then rotating around J4, and we end up around 249 pound-inch. For J5, this is a different scenario where, because in a competition, we are using 15-pound payload, and the grippers in J5 will be holding it, so that's going to add up the weight together around 17.98 pounds. And the R represented in J5 is being shown as the radius of the J5 assembly, and as a result, we end up with 35.96 pound-inch. Of course, that summary, the first bullet point is wrong. So after we submitted the PowerPoint, we were able to reevaluate the J1 and torque. We end up around 1,949 pound-inch, and it would make sense because like it has to take account like all the weights in J2, J3, J4, J5, and the 15-pound payload and the distance that is taking the point around J1. And then by using those torque requirements that we want to verify the stepper motors and the leader actuators that we currently have right now and compare the values we have, and then that's where we decide the specs of it. And the other 2 points that's not mentioned by the request of the
Test the motors, that's how you specify the specs. So if a motor puts out a 4-pound torque, like, yeah, that's the motor, we need 4 pound of torque because we have a motor that does that. That's what that statement sounds like to me. Or am I misinterpreting that?
I apologize, I'm going to repeat that. So when you mean verify empirically stepper motors in linear actuators, we're like calculating the torque that's like from like motors and actuators themselves and start comparing the values from the torque required. And then whether like the...
But you already done the work to identify the torque required. Why test and we can look at the spec sheets? That's what spec sheets are for.
It's a misrepresented statement, that's what we're referring to. Knowing the required torques at each joint location, we can then use that information to determine the appropriate motors for each joint location.
All right, that's a total 180 from what's written up there. And then second, like this says that you're going to verify motors. You have verifying empirically. That's basically I'm going to test it to make sure what it is, and then based on the test, based on the results I get, that becomes my spec. Like that's like the opposite of what we're supposed to do. You have to identify motors that meet the requirements. That's what you have to do. Second, what about linear actuators? So you computed the torque. Based on the mounting, what forces are we expecting to see for J2 and J3? Because again, are you gonna see the actuators work? Well, the ones that we have clearly work. So you verified that empirically several times by operating the arm. But what exactly do we want to size up the actuators to be? How much force do we need for J1 and J2? And if you have the torque required at that joint, how are you going to size up those actuators? And this is not a rhetorical question I'm asking right now, but what do we need to do for that?
Actually, like checking out the specs of the linear actuators, and then
But how can you check the specs when you don't have you didn't present a force requirement? You didn't demonstrate what the force output needs to be. You can do that for the motor, you can do that for the actuator based on the evidence presented. If you go back to every slide, you just have force. That's fine. That's good for a motor, but linear actuators don't work on it. They work on displacement and force. So what are you going to do to get that force output required? And you can't say testing because that's not what I'm asking. Are you going to determine the required force output from the linear actuator?
What I was going to say, like the linear actuators, like the values, I'm still figuring out like the governing equation, and just looking
That's
at
problem. Civil wall forces is equal to 0 in the x and the y direction. Those are the governing equations.
As far as determining the actual force required in the stroke of the actuator, the simplest way to do that on paper first is to consider the required torque in each joint, work that backwards as though we're solving for a force in the distance that the linear actuator is positioned relative to where that torque occurs.
Now, what you got to remember is you have to use an inverted slider crank mechanism because you have essentially a 4-bar linkage, and that is moving. You have two members that are moving. So based on the target output torque at that joint, you have to figure out what the target force output is. But you can't test anything until you select it, design it, build it, and verify it.
thank you for the feedback, Professor.
Hello, everyone. Hello, everyone. My name is Miguel Beto. I'm working on the Ripper this year. The main problem we're trying to solve is we're trying to figure out the linkage must be able to withstand the tension and the bending being induced by the 15-pound payload. And we're also trying to make sure that the materials wouldn't deform after being exposed to heat for the duration of time. And our design parameters, we're focusing more on the yield point and the glass transition temperatures. Please ignore the Young's modulus since we never had to include that during calculation. And as we mentioned before, last year's linkage accidentally broke down, which cost us.
You said that the Young's modulus don't have to consider it during the calculation.
We never had to include it from what I had to do. And as I was saying, during one of the linkage that I will explain later on during one of the slides, accidentally broke down. So, in fact, if you focus on the point 0, it's experiencing a force that no one technically considered during operation. So I was trying to figure out how much force would be applied being induced by the 7.5. And the reason it's 7.5 is because each gripper tip is supporting the payload, which is going to be symmetrical. So each gripper tip will be experiencing half the load. Oh, you have a question?
Right there. So you're saying a safety factor between 2 and 5? That's kind of a big range.
Yes, I understand.
That could kind of really, I guess, change your entire design, whether or not you're doing 2 and whether or not you're doing 5. Are you like leaning more towards 2 or maybe more towards 5?
I wouldn't mind leaning more towards the 2. It's just that sometimes the material that we select also
won't be able to experience the temperature, like sustain it while still being operational.
Size it. Make it bigger or make it smaller. 'Cause right now, if you have a safety factor of 5, you're making it 2.5 times heavier than it needs to be. And guess what? That's your gripper. That's at the very end of your arm, which makes a bigger moment requirement or torque requirement for everybody else. Make everyone else's life more difficult. That gets amplified bigly when you have the gripper. That's why lightweight is very critical. Safety factor isn't like, oh, I don't know, you design, you work to hit that number. That's how you vary your design. It's a target that you hit. I mean, when we had this discussion between 2 to 5 already. You try to go to the limit that you feel it's safe. 5 is, I mean, civil engineers work with safety factors of 4 because they think of like, oh, what if a really crazy storm hits all of a sudden? Just to give you a concept of safety factor scale.
I understand. I agree.
Well, come on, we gotta do better than the civils.
Yeah. What's the current safety factor of the gripper?
I think it was approximately, 3.62. It's in my notes right now. I don't have it in the slides, unfortunately. Last time I checked.
Okay. That's all.
Thank you. So how we were able to figure out how much force was being induced by that linkage, do you have a question? So we figured out the stress was being applied during that gripper chip was approximately going to be around 61 psi. And now we were able to figure out the moment. Some of the moments we set to 0. So we took the horizontal distance between 0.3 and 0.2, which multiplied by the force, and the same goes with 0.3 and 0.0.
Is this a linkage or is it like?
It's a linkage, yeah, unfortunately. We only focus on the half because the other half is pretty much going to be the same.
Yeah.
It was.
So this is a linkage. What's holding it in place? So I assume it's a linkage, but you're assuming the actuator is holding everything in place. So when it's hitting something, 7.5 pounds. So,
All of our linkages are put together by a
so yeah, but you have 1 degree of freedom. But the actuator is holding it, if everything's basically locked in position. So we're assuming a rigid body overall. Okay.
I only did up to this point because that's mainly our main focus on right now is just that thing alone because that's the only one that broke down during competition. Everything else should still be along.
But what kind of failure did you see? Because if this is a linkage, and I hit 0.2, I think it's going to deflect. What's going to be taking the load would be the servo, the holding torque of the servo. So the force has to basically be greater than the servo holding torque. And then what's going to fail first is the servo will deflect.
The reason
and the
why
linkage will survive.
The reason why we're so interested in 0.0 is because during competition last year, that was the one point of the gripper that actually failed.
But was it a direct impact like that? Because I feel like it was deflect. It just induced the load to the holdings to the servo.
We believe it was the result of an impact load and just due to a exposure to the elements. Just because of those,
it's like it's worn down.
Yeah, so because we all know that different filaments have different flash transition temperatures, and for that reason, we're also interested in the flash transition.
For me, it was like it got brittle.
Yeah,
impacts.
Exactly.
Which is why we had a high safety factor because you guys to include flash transition temperatures.
I mean, once it transition, it's crap. Like, you got to replace it.
Mm-hmm.
What it is, it turns brittle, so brittle materials can't take impact loads. I mean, that lug is pretty strong if I stand on it, but if I drop it, it takes me to shatter.
Yes.
It doesn't have the energy absorption capability. So what you gotta do is, one, you gotta select the material that won't have that transition, then size it. That's the first thing you do. You make sure you work with something that doesn't have that glass transition within the range that you operate under. And if this is an impact load, 7.5 pounds seems like really small for an impact load. If it's an impact load that broke it, 7.5 pounds seems kind of small for an impact. I don't know how big, but this impact loads tend to be a lot bigger.
Static evaluation as of right now, which what I believe against assassin is still the actual sort of sway, because the actual procedure that was in place when this piece failed was that rover's moving from point A to point B, and there was a sway on the arm, and right before arriving at point B, that particular point B linkage itself failed. The pin did not. And so the other areas of interest for us are not only, as we've been talking about, material glass transition temperature, but also whether or not there was a life cycle on it. We don't think that was the issue though, because up until this very point, that gripper had been subjected to its load no other times. As in, it was literally put together and testing to be done. Unfortunately, in this regard, I apologize for veering off of the main topic. When it comes to empirical testing on the materials that we have for the gripper, that goes to the functionality of it, and those seven motors are always give our electrical controls team trouble. But because it failed in such a fashion where it had not been subjected to a load prior, it had not collided. It was a matter of, if you will, sway, internal force, and essentially cracking what we suspect. We're trying to see if it has to do with the material exposure to the environment, or perhaps even the manufacturing process, because there could be near parts.
Yeah.
So.
One of the main failure modes for the component that you're talking about is that the layers delaminated. That was one of the key factors.
It's pretty frequent with 3D printed parts. What was the fill bulk density on that?
100%. It was not ABS or PLA, it was SLA. It was from one of our old members. We had access to a much higher end 3D printer that produced very high accuracy parts but very low strength parts. And so it was a mistake that part made it to competition. We had printed it that way to test for dimensioning and seeing how much, if our dimensions were correct.
For that, we want to print out several linkages using a variety of filaments, exposing them to different amounts of heat, and then testing them with the inertial machine, or sorry, a MTF machine. And that will lead into prototyping manufacturing.
I'll start off with the mechanical science system by going over the auger that will be for the onboard soil sampling. So the kind of problems that we'll be expecting for the mechanical side of things for the science task is that we need to penetrate a rough topsoil to retrieve a soil sample for our onboard analysis. That means our mortar should have a fed RPM sufficient for soil travel into the collection chamber. But because of that RPM, we also expect some torque to be generated, in which case the forces acting on the auger may or may not be a factor in which the auger will fail. So we need to produce an auger that will not fail during this penetration. So some of our design parameters that we're looking at here is a gear ratio that is to be in a gearbox paired with the motor. Due to the inverse relationship between torque and RPM, the pitch of flights on the auger also play an important role for soil traveling upwards into our collection chamber and our soil cache. And then finally, the forces acting on the blades as it impacts the topsoil for soil penetration. So some of these numbers that I'll be going over today are the following. So our RPM versus torque, we need to achieve a minimum of 200 RPM with a torque code of at least 30 foot-pounds. The forces that the auger is expected to withstand is upwards to 100-pound force on the outer radii of the auger on the flights, but in this case we'll be looking at the blades since that will be the main point of contact between the auger and the topsoil. And then whereas upwards towards the center of the auger, we're looking at max 300-pound force. Our factor of safety needs to be at least 5 due to the fact that we're looking at a worst case scenario in which we may be penetrating a clay-like substance. And finally, our soil travel should take no longer than 10 seconds due to the fact that within a time span of 30 minutes, we are expected to look at upwards to 6 different testing sites, one of which may be a rock. And we need to collect soil within a sufficient amount of time in order to conduct an onboard analysis.
Is your 100 bending mode?
Sorry, pound force. So, starting off with the torque versus RPM, there is a slight mistyping on there. That torque should be, the torque output is equal to the motor of the torque multiplied by the gear ratio of the gearbox. And the RPM, well, that's exactly what you see on there is the RPM of the motor divided by the gear ratio. So this is assuming that our motor is running at peak efficiency under a load as it's going downwards into the soil. And so these values that you see right here are as they have been taken from looking at a spreadsheet provided by the manufacturer. Now this graph you see here is just a motor pairing with various gearboxes. And if we zoom into here, this is actually a formatting problem on MATLAB's end. That bottommost corner that you see that's labeled, that's actually our 81:1 gear ratio, whereas that middle indicator, that is our 69:1 gear ratio. They both exceed the 200 RPM requirement, as well as hit within the range of our 30 foot-pound requirement for the auger to be experiencing any sort of forces acting onto it for the torque. So taking some of these into mind, first we'll look at how the torque plays a factor into the auger for forces acting on it. And this is just looking at that outermost radii of the auger. So this is obviously a solid stem auger. As you can see here, as we have a fed torque on the free body diagram acting on the auger, in which case this will be at some point along the face, on the blade. We are expected to be hitting a force at an angle as we're penetrating that topsoil. So looking closely, the 69:1 and the 81:1, they're still within that range of what we want to see. Our torque inputs for both of them hit underneath that 100-pound force requirement of the forces expected by the auger.
Where does the gear ratio come into play here? Right now, I can see a balance between torque and the equation for the torque, but how does that's the torque about the point of rotation, not what's happening at the end. So how does gear ratio play into this? Because you have an R sine theta, so to me, the parameters here is the moment arm or the angle which the forces project on that arm. I don't see how you can get the gear ratio out of that. There's no gear ratio in there.
Well, the gear ratio kind of contributes to the torque that plays. So kind of the basics of kinematics and mechanical design is that with your torque supplied to one gear throughout an entire gear ratio, your torque is just multiplied by that gear reduction, whereas the RPM is kind of the opposite of that.
Well, you're conserving power, but where are we looking at the torque value? Where are we taking this torque value from?
Torque value comes from
at what point are you looking at the torque value? It varies throughout the system, but at what point are you getting this plot?
So this one is at the outermost radii of the auger. So basically, just at the very.
That's away from the gear ratio. That's at the point of contact. That's what the force is. But if you have a torque, what the torque has to be, then it's not that. I'm saying, where are you considering the torque output? Is that output from the gearbox, output from the motor, output from the auger? Like, where is that torque being measured at? That's sort of where I'm confused. Because
if I'm looking at that schematic, and I'm gonna say schematic because it's not a three-body diagram, you have no axis, you have an arrow. There's no gear ratio there. There's no point A, point B, which I'm taking the moment or the torque value. So when I'm looking at this, I'm asking, where does the role of gear ratio play? Because the equation you have has nothing to do with gear ratio. It just relates to the torque at a point as a function of moment arm and angle of projection. So where does gear ratio, how do you get these curves ultimately?
So these the torque values that you see along the x-axis, that was calculated previously within our RPM torque, and the gear ratio did play a role in that, due to the fact that there is that inverse relationship that you have to me back in conceptual design. So it's just a matter of applying that output of the torque from the motor to gearbox combination into the auger as it's spinning.
So are you saying, depending on what the output torque is from the motor, or a set radial distance, or really a set diameter of the auger, what the force output's in?
Yes.
What about if you go with different radiuses of torque?
I'm actually going to be touching up on that in terms of the radius, but in this next case, it'll be more of applying one of the torque values, which it will be in this case the A101. So throughout the auger radii, you see towards the center this force output, in which case it's acting on the auger, whereas outwards towards that outermost radii of the auger, it decreases overall. So based on our gearbox that we have, due to that inverse relationship between the torque and RPM, we can see here that with our torque, this is our best most case for the forces acting on the auger.
How do you come to that conclusion? How do you come to that conclusion?
For the forces acting on the auger. This is just assuming like the worst case scenario in which we would be encountering a clay-like substance on the top.
Is this the force that's acting on the auger, or is this the force created by the auger?
This will be the forces acting on the auger as it's.
So if that's the case, what radius are you looking at?
In this case, this is just the radii throughout that blade. We were seeing this from near the center of the auger, where you would have that first bit of the blade, all the way out towards the outer radii of the solid step auger.
Okay. But I'm not following how this could be the force acting on the auger. Because if you're going to tell me about forces acting on the auger, I'd expect to see some type of frictional loading, contact loading, anything where you're cutting the material. Whereas here, I think this is the output force capability of the auger. Saying that the biggest, I wouldn't even say force, is the biggest bending, is what you have is a shear load on the auger. On the surface of it, you have a shear load, and that's existing the force output of the auger. So what you should have like a bending. I'm not sure what the force is doing. I'm not sure what the actual force. But I would expect to see something more like a bending force. And from looking at this curve, I don't understand how you come to the conclusion that this is the best possible blade. Because what's the metric that you use to make that decision? But if this is just one blade design, it's just looking at the load distribution across the blade. It's not looking at different blade designs and the load, the peak loads at the extreme. This is one blade design, and this is just not even the distribution. It's like it's out. So it's not what's happening to the blade, it's what the output from the motor to the auger is doing on the blade. This is what it could stand. Not necessarily what it could provide. I even could stand what it could provide. So that's where I'm not sure if this is, because if you're going to say that this blade works, you got to show me what the load scenario, what the critical stress is, not necessarily the capable output. You haven't taken into account in terms of like the resist, like if this is the force output, it needs to be a reacting force.
that is stressing the part. Otherwise, if it's free to move, it's just what you can provide. It's not just subjective.
Yeah. Thank you for that, Professor.
So I'm not sure how this curve meets that conclusion.
Thank you for that, Professor. So now looking at the factor of safety, these are valued, first off, this is just looking at one material, whereas previously we had initially a comparison of different materials from thermoplastics upwards to commercially available materials. So what you just see right here is aluminum at the moment. And these are, and so the kind of factor of safety that you see here, these are from the forces that we have calculated previously in the past slides. I can compare that to the overall area of the blades right here. You can see the kind of the basic geometry of that on the screen. So the thing is that this auger, for the most part, that we're looking at is something that's commercially available, and something that we also have noticed while working on this is that, for the most part, almost every single commercially available auger that you can get at like a Home Depot or Lowe's or even Amazon, they all have this very similar blade geometry. So these are the forces that are acting all across that radii. And based on this, our factor of safety, we are saying 5 because we do expect some deformation as we're penetrating that topsoil. But in terms of the functionality and the collection of our soil sample, we don't expect this to be compromised whatsoever. It's just a matter of, will this be able to work even though the auger blades will be undergoing some sort of deformation based on the forces acting on it, depending on the material. Aluminum, you can see here, between the minimum and maximum of factor of safety. That minimum value is based on a higher force concentration near the center of the auger, whereas that maximum factor of safety is outwards towards the auger on that extreme radius.
So right there you have basically an axial load, either a normal load, pressure, or tension. How is it acting on the blade? How do you see the tension or compression being as a primary mode of failure on this guy? So how do you envision this? Where's the stress, the direction of the stress?
Direction of the stress will be concentrated on that face that you see. And also something to note that this is a face that the geometry remains consistent throughout the plexus is going up, but we're just looking at this one particular part because that is where we expect the most force, kind of the most forces to act. Mm-hmm. Whereas our expected failures was big. So
basically on that tip, that front face is where you expect some biggest load failure.
Correct.
What about the outer wall when they're drilling down? You don't expect that friction between them?
No, sir. For the most part, that face that you see, that's expected to break up that topsoil, and it's not exactly going to be like that perfect circle as you break into the topsoil. The entire area around it, we don't know how far that would reach, but that becomes broken up.
It's a softer soil and it's collapsing onto the auger as it's drilling it out. Once you see the outer surfaces, they're being subjected to friction and the weight of the surrounding soil. So you have this original load resisting the motion of the auger. Just imagine, I've gotten real bit stuck in material more than breaking my tips off, especially if it's softer material. Like, drill a plastic hole and you see how hot it melts and gets stuck and you get shear load on it. It's torsional loads and shear loads that break these types of mechanisms, not the impact load on the first one. I mean, that's not a purely compressive force acting on that thing. I can see now what your analysis is doing, but that's not going to be the primary mode of failure. Because if your auger fails, it's going to fail at the weld where you have the helix attached to the shaft. That weld will be the part that fails. Which means what that's going to be subjected to is some type of bending moment, some type of shear load at that point. That would be the point of contact where it fails. This is not going to fail. It's probably going to get damaged and worn down, but it's not going to have a failure where you can't operate. most critical failure would be that the outer spiral will get separated from the outer shaft of the auger. And that's not a normal axial load. It's some kind of shear load due to the torsional resistance from the surrounding material. Or even if you're pushing on that guy, it's inducing the shear load at that point of contact. I agree there's a force acting on it, but that's inducing a shear load, and that area is probably really small of the auger. So that's going to be your main point of failure, is that point of contact.
Where the well is.
Where the well is, yeah. And then you can directly raise the output port. In worst case, the output port is installed out the motor, so you can't rotate anymore, so you have a max port output. You gotta make sure that the entire well can take that shear load. Because then the surrounding material is just gonna resist it. It's not going to provide anything more than that.
Thanks, Professor. So last thing that we're looking at is the soil travel upwards into our collection chamber and then therefore our onboard soil cache analysis for the lab sciences bit of the rover. So back when I mentioned RPM, we have these values for the 81-1 and the 69-1. So in this case, we're looking at the 81-1, and this is where we convert our RPM into an RPS, and then we have to look at our travel time in seconds. So we have to divide the number of rotations by our RPS. Ignore that second typing that you see right there. But for the most part, we're looking at that travel upwards based on the amount of rotations that we have going upwards on the auger. And again, this is, as I had stated previously, this is based on a commercially available auger. And this is something that we actually have in prototyping, which I will expand on later. So as you can see from kind of this diagram, as the auger is rotating in a clockwise fashion, doesn't really matter, but we'll say clockwise because this is what we are currently working off of. We'll be digging downwards, and as we're digging downwards, as that soil is breaking up, it becomes this softer sample, in which case it'll fall into the hole and then travel upwards. And so with that provided amount of RPM, we can see how fast we're getting the soil travel upwards into our collection chamber. Again, as I need to emphasize that we are under a 30-minute time frame to conduct our soil sampling on site, as well as testing for life sustainability, as well as any sort of life protection.
How much more breaking does that first part of the spiral break? If you have that head that seems to go in about an inch further, or a diameter length further down, that breaks up the topsoil first. How much of a role does that top part play? That first part of the spiral?
So that top part, think of it like kind of a center drill where it kind of makes that like a pilot hole, and whereas as we're going down, like we don't expect to do this like a sort of just continuous dive in. We're expected to do this as a sort of tech drilling operation. That's if there is mainly to break up that little bit of topsoil and also to provide a sort of guide hole for it to go downwards. Something that I failed to mention during this explanation is that what you see here in terms of that casing covering the auger, not only is that supposed to help in terms of the soil travel, but there should also be at least one rotation of flights exposed, and in that way we can have this Archimedes screw concept in play in order for our soil travel to happen.
Does the auger go further down than that outer cylinder?
Yes, it does. But we don't expect the cylinder to be undergoing any sort of forces or moments. So, a kind of status summary on this is that our motor and our S550 is expected to be paired with an 81-1 gearbox. We do have a secondary backup of a 69-1 due to the parameters. The auger composition is expected to be made out of aluminum or, if exactly needed, steel. And the way that we have planned to approach the manufacturing of this based on composition is either a timely multi-milling process, or doing TIG welding with a rod to a set of aluminum sheets to a set of sheet metals that will be wrapping around the auger to form the pitch and flights. So some research that we still have to do is discerning how the travel distance and the pitch of the flights also contribute to that travel keep in mind that what I did with the rotations is just it's just a number of rotations based on what's commercially available. We aren't exactly certain whether or not the length and the pitch as well as the angle plays a role into that, and if it affects our time. So that's something we have to look into. We also have to look into another thing that we have to look into is testing with various soil conditions, because with URC they say that we have to test with upwards of 6 soil sites, but we don't exactly know what the composition is. So this could either be consistent with something on Mars, in which case it would be consistent with the desert-like region of Utah, or they may have their own soil samples, in which case we may expect something more Earth-like, so to say. And finally, something that we are currently looking into is the soil volume flow from the chamber to the analysis box, in which case the auger plays that first part of that soil volume flow. Some prototyping that we are currently conducting is one we already have an auger that we are running tests on, and the motor and gearbox is expected to be coming in soon. Our soil testing based on our motor and gearbox pairings will be done sometime around November 11th. And finally, our soil volume flow, we anticipate to be hammering that out starting the first week of December. All right, so I'll be talking about the chassis mounted system, starting with the backplate. And so here you can see the current design that we have for the backplate, and we are going with a 2D truss-like design, so we can reduce the amount of weight while keeping the structural stability that will be needed for the auger system. And so you can also see the mounting points for each of the components that will be attached to the backplate and where it will be mounted to the chest. So the main objective for the backplate is to provide mechanical stability for the auger system and to allow for mounting capability to the chassis. For the design parameters, the backplate must withstand vibrational forces generated by the auger and bending moments from all the attached components without yielding. And so the strength to weight ratio is also going to be very important, because we want to reduce the amount of weight while we are trying to meet our weight limit at 38 pounds for the entire design system, which includes the chassis mounted system and the onboard soil analysis box. And we're going to need it to maintain the strength to hold all these components, as it would be roughly around 20 pounds for the entire chassis mounted system.
Would you say that these two previous ones are requirements, not so much parameters? The first one does say requirements, not a parameter. You can't control it. You design for that. And are you going to vary the strength to weight ratio? Is that what you're telling me?
Yes.
So you're going to have that be a variable here to see what the output is?
So we can change the thickness of the backplate and the
thickness would be a parameter.
Okay. And then
Also,
also
none of these things, unless you write it as a strength to weight ratio, it's just kind of not things to vary versus compare. It's a hard thing to make that argument. The parameter is thickness, that's what you're varying, that's a parameter. The first one's a requirement, the second one would probably be a performance criteria. Thickness would be your one parameter.
Yeah, like the geometrical cuts.
Or those are things that you can change in your design. These are not parameters.
Performance criteria. Our backplate must withstand the total weight of the chassis mounted system, which is going to be around 20 pounds. And so that's the static case, and when using the center of mass of each component that are being mounted to the backplate, we can translate those forces back onto the mounting points for the backplate to the chassis. And then for the dynamic case, it's got to remain structurally stable for auger drilling, including the rotational force of the auger and the linear motion of the mounting plate as the auger is being driven into the soil. And so to do this, I will be using ANSYS to determine the forces that will be encountered by the truss-like design. So here you can see the simplified reaction forces that will be affected on the back plate. And so they're just shows one point that they will be acting on, whereas they will be translated to two different supports that they use. And then using all of these reactions, we can translate those to the mounting points to find the reactions at those mounting goals, and then use those to test for yielding and stability. So essentially the figure on the right is in front. They're going to be on both sides of the auger. It's just a linear support rail which will cause the mounting plate, which the auger is attached to. It just eliminates the rotation of that. And so I just moved it to the right side so you can see the auger system a little better. And yeah, so then you can see in this picture I have the auger protruding from the cylinder as well.
So are you looking at how the thickness of the plate can withstand?
This is just purely looking at the forces generated by the components attached to the back plate.
So what's happening to the plate? How the thickness of the plate affecting all of them? I guess what are the forces that the plate is feeling? Because that's sort of what you're designing around, right? What the plate is doing. So what's the plate being subjected to? Assuming that's what that guy is on the left, far left, with that thin plate. What is that guy experiencing?
The bottom moments and reactions.
Well, what's happening on the plate? So how is the load path affecting the plate?
It's capturing a bending moment and a compression.
I don't see how that plate would have a bending moment.
All the attached components, they're going to be bending the plate forward or towards the auger. Because essentially the mounting points will be mounted towards the
You have, what thickness of the plate are we estimating so far?
Right now it's at an 1/8 inch.
What safety factor do we have at an 1/8 inch?
That is determined with the policy. As well, I will be varying the thickness.
You can't just compute the moment and say times thickness over moment of inertia?
There's still a couple design factor issues that we have to deal with before I can get those final calculations for the moments. There are a couple like weights, and with our prototype auger, it doesn't exactly fit within the chamber and to like it shows.
Yeah, but you can estimate some loads. You may not know what the dimensions are. You can estimate some basic forces. You can start sizing it up.
So the backplate will be made out of 6061 T6 aluminum.
How do you know that? How can it be aluminum? How do you know that that's the material types?
I did a trade study with some different materials, and it came down between 3 different aluminum alloys. There's machinable plastics that would be easy to use, however, they wouldn't provide enough strength.
Or you don't know what your strength requirement is. You give me no safety factor, no strength to weight ratio, so you can't make this conclusion. How do you know how much weight you're going to be reducing if you don't know what the target strength needs to be? You can't make this conclusion without telling me what the stress is induced by that scenario. And it's picking a material that's strong that in a thickness combination that meets that requirement and computing to the corresponding weight limit. Since you haven't done that, you can't make this conclusion. Maybe the material, yeah, you can pick one because that's what you don't work with. You can't definitely not make the argument for the thickness, for the weight reduction. There's no support for that.
It's strictly based on volume. So
Well, how do you know that volume is enough? It could be insufficient, could be too much.
That's true.
You can't make that argument. I get where volume, yeah, weight, high density, weight density, volume, but ultimately,
you don't know that that material is thick enough or thin enough. You haven't told me how much that thing's gonna flex, what the stress is, but you have a freely supported cantilever beam ultimately. That thing's gonna flex, potentially. So, you may not care about, it may be strong enough, but you may have some flexing problems, because that thing is not supported the way you've drawn it out. So what that means is when you start drilling down, this is gonna start flexing this way. So your angle, your hole's gonna start going at an angle. That's what's gonna happen. Either that thing flexes first, or B, the hole starts going in at an angle. One or the other is gonna happen, the way it's drawn out. So things you should consider besides thickness is lateral deflection. That's probably gonna be more important, if you guys care about that. But it's definitely gonna start flexing. And as soon as you start deflecting it away from it, guess what? The bending moment gets bigger. So you get some minor non-linear.
So, starting progress, trying to come up with the final calculations for the moment forces captured by the mounting points to the chassis. Forces captured from the dynamic motion onto the backplate. So for the probe arm, we can see its design. And so it is designed to allow us to use the soil sensor in order to measure the soil temperature, water moisture, and electrical conductivity of the soil at each site that we'll be collecting samples. And so we'll be using PET-G printed parts and 606126 aluminum square tubing. And so essentially it is made of hollow, it's all hollow on the inside in order to allow the cable to run from the sensor to the chassis.
Is there a reason why it's
So right here it is it's to allow the soil sensor to rotate beneath the auger along its linear axis without interfering or hitting the auger system itself. And so it is also to provide rigid support for the insertion process of the sensor into the ground soil while we will be taking those measurements for our science analysis. So design parameters, rotational motion must avoid the auger system, which is why we have those 290-degree bends. And gravitational forces at the mounting point will be, and that's not necessarily a parameter, I'm sorry, and that will be affected by the motor mount that we will be using to avoid yielding. The torque required from the separate motor for the arm will be a parameter as we will test different motors to be used. So the torque from separate motors should be able to rotate the probe on 180 degrees, and with our initial assumption, I was taking the probe arm and giving it 5 seconds to rotate from completely vertical to completely upright to down, and each component should not encounter any deformation. So here you can see
about permanent deformation or elastic deformation. Put a logo on it, it's going to, not however small, it's going to be small.
Plastic decoration.
So what's your safety factor?
The material.
For your design. You would know that if you specify a safety factor. What's your design safety factor?
1.2, 1.5 in that area.
You should have one ahead of time, so when you start looking at your stresses, you know how thick the material needs to be. Not the other way around. If you design something, you want to know how thick should I make it. So you pick a safety factor. You should always, no deformation means there's no load on it. That's all that's means. No plastic deformation, you have to have a safety factor for it. But without that safety safety factor, you won't know how thick the material's going to be. 1.2 to 1.5, that's a huge range. That's kind of big.
So for the probe arm, the torque required to rotate the probe arm from 180 degrees. Here you see this graph from negative pi over 2 to pi over 2, where negative pi over 2 is facing downwards, and then coming all the way up to pi over 2 facing straight up, whereas we can see the maximum loads will be encountered at a point that is completely horizontal. So the acceleration torque, it is giving 1 second to accelerate to 6 RPMs, which gives which then rotates the probe arm 180 degrees in 5 seconds. And so using the equation you see here and adding a safety factor of 1.2, the required torque would be 1.17 pound-foot.
What is load torque and what is acceleration torque?
So load torque is just the amount of torque that it will be encountered just to hold it in place and without any motion. And then the acceleration torque will be the amount of torque required to actually move the probe arm.
Now, how fast are you trying to move the probe arm?
Right now it's designed for 6 rotations per minute. So it's not very fast. 100 degrees in 5 seconds.
But if that's a steady rotation, how does, if you have steady rotation, then do you necessarily care about the acceleration torque?
It started from being at 0 just to getting to 5 RPM versus RPM. That's why you can see it's pretty low.
Why not look at it from the conservation of energy, torque times omega, if you look at omega, and look at people who 1/2 omega squared is the moment of inertia, and see what the torque output is to maintain that rotation. If your stall torque is greater than that, then you're gonna have enough torque approach. You gotta look at what you're about. I'm not sure what these two figures are doing. You have an acceleration torque that's 1 order of magnitude smaller than the low power. And you gotta give me motors that are orders of magnitude above this. So you're gonna have enough force to rotate. Your factor of safety is going to be way bigger than that. You just have a 60-foot-pound that's going to be gearbox.
This is the probe arm, so we need a separate motor that's separate from all the
Yeah, but you gotta look at the moment of inertia, what that does, and see if that, whatever that moment of inertia is plus the weight of it, what kind of a moment does it induce at the motor? And instead of looking at the variation in the angle, we all know where the peak torque is gonna be from perfectly horizontal to get the maximum effective gravity action. That's when your angle equals 0, that's to get the maximum. So if you get the maximum, you're fine, you don't have to worry about all this other stuff. You just basically have a sign point. Look at the max requirement and see if you can max it. So what you have to do is make sure that you have a holding torque that's greater than that. The stall torque of the motor has to be greater than that or holding torque. Then it should be fine. But you need to look at what the moment of inertia is. Because then I don't know where these other torque values are coming from. You haven't factored in the weight and the design of your probe arm. I don't know what the holding torque needs to be from
motor. Yeah, so that is one thing I didn't add in. There was a free-body diagram of the center masses of each of the components.
That basically will tell you what the motor's gonna be driving.
Yeah, that's how it came up with these graphs. Not that code, those equations.
Like sine functions. You gotta look at the worst case scenario, which is when you're next horizontal. You have the biggest moment on the motor. If the motor can survive that, then it can rotate.
Yeah, that's,
You wanna look at the RPM requirement, you will power requirement. And then you go.
so I use the maximums from each of these graphs, add those together as TL and TA. With the safety factor, it came out to 1. Rope arm will be made of 6061 T6 aluminum square tubing at a 0.75 per 3/4 inch and PETG printed parts. We use a Newman 23 motor in order to provide on the torque. And the stress calculations on the elbow joints and motor mount are currently in progress to determine if there will be any cost information or not.
What about the moment,
Yes.
what about the stress calculation on the entire robot? That's kind of close. Yeah, 90-degree bend, that's gonna flex easily.
Yeah, that's why the elbow joints
Yeah,
are still in the form.
You gotta make sure that it's great, especially if you have an 90-degree bend, that's not pretty. So each of you basically have a series of cantilever beams. This is like easily.
All right, so I'll be talking about the fluidics side of the science system. Just get into it real quick. Our problem description. As per competition requirements this year, we'll have to analyze up to 5 soil sites, and there will be at least 1 rock sample that we have to analyze. So when analyzing the soil sites, we'll have to transport soil from the ground to onboard the rover. And once it's onboard the rover, then we need to transport liquid to the soil sample. The reason for transporting the liquid is so that we can do a chemical reaction with the soil, and then that chemical reaction will tell us if there's key lysosame compounds present in the soil. And then of course, we also want to take microscopic images. So the two fluids that we'll be using to transport inside the analysis box will be an acid. Right now we're looking at hydrogen peroxide. We're considering hydrochloric acid as well. And then we're also transporting water. All right, so for our design parameters, we'll be using a linear actuator to compress 3 syringes containing water and acid. And then that linear actuator will be pushing on a force distribution plate, which is in turn mounted to the 3 syringes. And we'll need a tubing network that distributes all this fluid appropriately to each beaker. This will make more sense when I show you guys an image of the top view of the system. The syringe diameter is going to be 1.75 inches. It's a big 200 milliliter syringe, so it's a very big syringe. The reason we went with really big syringes is because you have to do up to 5 soil tests, and I want to use ideally 1 syringe per gear so that we can do it 1 syringe for all 5 tests. And we're looking at a 3-to-1 parts ratio. So if we have 1 gram soil, we want about 3 times as much liquid per soil. So that's the reason for the 200 ml syringes. Our performance criteria, we want to find the force required to compress all 3 syringes. And then once we know that force, we know the initial velocity of that liquid, of the plunger. And then if you know the initial velocity of the plunger, you can find the exit velocity out of the syringe. And then you know the flow rate. And then from there, you can divide your the volume you need per beaker divided by the flow rate, and it'll give you the time required to fill the beakers. That's important. That's an important value. We want to know the time that it takes to fill the beakers, because then you can program the linear actuator to be on for let's say 1 second, turn it off, so you get an accurate amount of volume per stroke. So here our evidence baseline feasibility. The simplest approach to this problem would just be to do a control volume approach, and you look at conservation of mass. We assume that the speed of the plunger will be equal to the speed of the actuating rod. And the viscosity is an important note here. The hydrogen peroxide viscosity and water viscosity are about the same, so they will be treated as equal. But if they weren't, then you have an induced moment, but we don't have that case here. And here's our governing equation. We know that the volume is at 0.1, 0.2, we're going to do the same. So if you look for an equation that relates volume to time, that gives you flow rate. And then the flow rate you can isolate for your exit velocity. So it's just the ratio of the two cross-sectional areas and the initial velocity. Here's our FBD of the system. We're looking at a linear actuator pushing on an actuating rod, and then here you've got this titled force distribution plate, and then you got your 3 syringes there. And then looking more precisely at each syringe, you'll have a force pressing down on the plunger, and then those 2 boxes indicate that the volume is equal on the 1.2, pushing the syringe plunger, and then you have your exit velocity, and then we can find everything else from there. There's a CAD drawing. This is a preliminary CAD drawing. So from the time that we posted this slideshow, we've done some work on this. The force distribution plate is not rectangular as it may perceive. It's a circular force distribution plate. And this will better displace the load of the actuating rod to all syringes. Also, the actuating force distribution plate will be mounted to the actuating rod with this little pin. You see there's a pin hole on the tip of the actuating rod. So we'll be using that to place a bolt in the nut through to secure the force distribution plate on the actuating rod. And you can kind of get a scale for the size of the syringes here. They're really big. I'm looking to scale down maybe from 200 to 150 milliliters if it proves to be a concern. But right now it seems to be all right. And one thing I want to note as well, question?
I have a question. Since your control volume is changing, how do you take that into account?
As the control volume is changing?
Isn't it pushing out fluid or whatever?
It is, yeah. So you know that if the plunger at 0.1 displaces 2 milliliters of water, you have, because it's not getting dispensed as energy or anything, all that mass is getting pushed out the exit tube as 2 milliliters. So whatever input you do from the plunger will be essentially how much liquid is going into the beaker. Does that answer your question? All right. One thing that I found through experimenting, there is a siphoning effect with the plunger, with the syringes. So as soon as you start compressing the syringe, it's not going to stop by itself. It's going to keep going until it runs out of liquid. And that's a problem because we don't want that. So we're going to most likely have to bond the plunger tip to the force distribution plate so that we don't get that siphoning effect, most likely through the use of Velcro, or if not tape. Here's a top view of the analysis box. There is a blank space in that bottom left corner, and that's going to be where we're going to mount the whole syringe actuating rod assembly. It's going to be vertical, so that means the syringes will be higher than the beakers, so it'll be assisted by gravity as well. So we won't have to worry about if there's any liquid stuck in the lines. It's all going to feed through gravity, as well as the pressure induced from the syringe. And here we have a linear actuator I spec'd out. I found a line of linear actuators. I was talking to our controls team, and they said they prefer a linear actuator with a feedback system. So the feedback system allows you to know where your actuating rod is real time. It's helpful. So I found a line of linear actuators that have feedback, and I chose the one with 35 pounds because that's going to be the least amount of force requirement. I did through experimental testing find that it takes about 1 pound per syringe, so we're looking at about 3 to 4 pounds of force required to compress the syringes. So we're not looking for a heavy duty linear actuator, we're looking for the smallest one they have. And then we're also looking for a 6-inch stroke as well. This is a typo, just to point out. The beam 1, it says 1.35 to 2 meters a second. It's inches a second. That's what it is on the graph. It should have said inches a second. But I did go ahead and convert it on this slide to meters or millimeters per second, just because it made the math easier. So here I found the beam 1 and then the beam 2, and then from there the flow rate. We know that our initial outlet speed will be about 2.75 to 4 meters a second, so that's pretty high. We want a high flow rate coming out because I kind of want to make the water hitting the soil mix the fluid at the same time. So if it's hitting at a high pressure, a high velocity, it's going to help mix the particles. We're going to have a flow rate of about 55 to 75 milliliters a second. And on the next slide here, we found our time required to fill the syringe or fill the beakers are about 1.1 to 1.6 seconds. This will all be determined experimentally because experimentally the flow rate is going to change due to the friction in the pipes. So that's an easy experiment we'll get to later. And then I found the Reynolds just to prove that it's really turbulent. It's about 20,000 Reynolds, so it's very turbulent. For our status summary, we need to work on designing and implementing the syringe actuating assembly. So that's going to include the linear actuator, force distribution plate, and then just make sure that we can integrate that with the analysis box that's already in place. And then I need to make the tubing network also. For the experiments, one of these has already been complete since the time we submitted this. The force on the plunger is about 3 to 4 pounds in total, about 1 pound per syringe. But I still need to know, once it's all built, the experimental flow rate through the pipes.
I'll be talking about the gear mechanism. So right here is just a general visual of what Will was talking about, 5 beakers on each gear. There will be 3 different kinds of scientific lab analysis on each gear, each beaker that's collected soil. As you can see in the red one, that is the driving gear, which has 7 teeth on it, and the driven gears have 28, so 41 gear ratio. An overview of the problem description is you collect soil samples and the beakers through a gear mechanism that will rotate to the exact position and location. And our design parameters are using input torque and the input speed. Input torque considering the stall torque of the base step motor and also the 4:1 gear ratio that we use. For the performance criteria, we want to see that the gears rotate as fast as possible to the most efficient position of each beaker. An example would be 96 RPM, and also relate this RPM to the pulse speed of the motor so you get the exact position of how many steps each beaker. For example, step motor with 1.8 degrees of a step angle is 200 steps per revolution. So for the driving gear, the red gear takes 40 steps each beaker. And so for evidence of baseline feasibility, we took into account the mechanical advantage of the gears, where the torque out is equal to torque in. You can see for the provided diagram that torque in will get torque out as well. So with the concept of the number of gear teeth proportional to its diameter, we can put that into the gear ratio and find out output torque as well. So the output torque from the stepper motor, we just use 45 centimeters. Just divide that by, or multiply that by 4, we get 180 centimeters for the driven. You can also use this concept and idea for the speed as well. So with an input of 96 RPM, you get an output of 24 RPM for the driven. For the plot on the bottom right, that is to show the values that are calculated from 90 to 105. And as you can see on the y-axis is the output of the speed being much lower. So with RPM, you can also relate that to the pulse speed based off the step motor. So for the driving gear, the red gear is 200 steps per revolution. For the driven gear, it's 800 steps per revolution, given the 4:1 gear ratio. So with the driven gear, it's 160 steps to each beaker. There's a typo. The 24 is supposed to be 96 RPM. Just converting that to 80 steps per second. Thus, it would take 2 seconds to get to each beaker. The thing that if it was 1 second, it would be too fast because the beaker would contain fluids and we don't want to spill.
How did you judge that 1 second? You didn't mention any requirement about
time. You said RPM for rotation, but if you're doing meters of fluids, how fast can you go before spillover?
Not exactly sure. We're going to judge the behavior based on testing those acting.
Just to be clear as well, the beakers are going to be velcroed or taped onto the gear as well to provide extra support.
Yeah, but what about the liquid inside the beaker? Can you throw that in?
No.
So why are you keeping them spilling over?
They're 100 milliliter beakers, and we're looking at about maybe a third of that being filled up. So we're hoping that we have enough clearance for the height.
How are you going to estimate that? And how fast of an acceleration can you get it before it spills over? You can calculate that. That's a big, very big problem. Chapter 2. If you don't specify what that delta T needs to be, then all these RPM numbers are just estimates. There's no basis for why these have to be the way they are. But I see this a linear slope of 4. That's fine. That's what 4 is. But there never was a mention that's filling the beaker over. And that's basically what you have to design it. That's fast enough, not too fast, where you can spill over to liquid. Because you have no container. It's not no sealed container. The Velcro is going to keep the beaker flying off, but not the beaker worried about. It's the actual liquid within the beaker. And there's no basis for saying that 96 is fast or too fast. It's
And I just have like 96, considering that it converted well with the steps per second. So,
I don't understand what
well, converting the 96 RPM to steps per second, you can input that amount into the value for the step motor code, and then each position for each beat.
So pick a different RPM, and all the gearing is exactly the same. I guess why does it have to be that fast? There's no justification. Your system, components sort of that definition. But when you presented this, you said it has to be 96 RPM. You should always work for it has to be 96. So you argued it had to be 96, and only did work to prove it has to be 96, but no reasonable comparison for why it has to be. So you picked it and you forced it to be 96. So there's no reason. That, to me, that could mean that 86 is the correct value. It could be, but your analysis doesn't show that. Or why a 4-to-1 gear ratio? Why not go with something faster and different gear ratio? Or vice versa?
All right, so then this month we'll consider the testing of prototyping and further analysis or more in-depth analysis of the gear mechanism, including the gear soils and fluids.
Now, open zero or anything gears.
We're looking into 3D printing it.
Do you know how many life cycles we need to see and operate those? Gear?
Not exactly. Besides the step motor and gear driving you. Other than that,
the other gears. The whole fluid loop with water.
yeah, those would be the most of the same.
The gear is supported by a thread tube. So I wouldn't be worried about shearing.
But I'm stuck on the floor to try to move all these other gears.
Oh, yeah, at the contact points? I can see how that would be an issue, yeah.
Because if you're moving it fast enough, you're gonna have this first movement and then resistance inertia keep going, so it's gonna be shocked little by little. And if we start making a little crack on that, one of those gears may come off.
Yeah, one solution to that would be to print multiple parts, the gears as well, so have backups, have competition for the rest of your own.
Design for it to not fail. That's
Ideally.
designing to fail. Versus designing for not fail. Why are you making that difficult down the road? If there's competition, the last thing you want to do is change out the gear.
I agree, yeah.
Task begins.
That would be a safety, a backup feature.
That's a
And
backup, but why does that, but
As
what
well.
I'm saying is you're designing it to fail.
we can also
Accepting
vary
failure.
the wall thickness for the 3D printed gear to
Yeah,
combat.
you gotta look into it before you build it. That's my point. There's ways to do it. You gotta know how thick that wall needs to be ahead of time.
So to overview our system plan, we are overhauling our mobility elements relating to the wheel hub, material reduction, the control arm geometry, as well as simplifying the motor assembly. And we are staying within our design constraints of that which is $3,000 and our weight budget of 44 pounds, as well as trying to keep the same ride height so that we can traverse in the same way that we know works. And I'm gonna give it over to Samuel to start talking about shocks.
So for the shocks, the objective is to find the effects of the shocks onto the system. The requirements are that it needs to help the suspension system maintain a ride height of 11 inches to 13 inches. This is mainly due to trying to traverse various terrains, and we don't want the chassis to be getting damaged by any of the taller rocks or other terrain. Also, the pneumatic spring of the system must support a drop of 1 meter, equal to 820 pound force. That is just on if the rover were to fall on, all the weight of the rover were to fall on one wheel. And for the baseline design, we're going with the pneumatic non-bite shocks with the NM AO42AR. For the design parameters, the air pressure of the shock, as it relates to the spring stiffness of the shock, and the displacement of the shock stroke itself. Another one of the design parameters are the forces acting on the shock, so the input force from the tires as it affects the shock itself. For the performance criteria, the stiffness K, pound per inch, for each of the different PSI, the amount of displacement delta X in inches on the shock for an input force from the wheel, and the force of the spring that is outputted by the input force on the wheel. So for the first part of my analysis, I conducted an experiment in which I loaded the chassis of the rover with the mock weight of the arm plus the 5 kilogram payload, and for different PSIs, I measured the ride height. And so 35 and 40 would not work for us in the system because we're trying to maintain a ride height between 11 and 13. And the reason I didn't go any higher was because that would make the system too stiff or too rigid for our terrain, which is, if it were all sand, that would be fine, but it's not. It's various terrains with rocky and boulders.
You use like static equilibrium, like embedded with
Yeah. Then for the second part of my baseline feasibility, I did a truss analysis of the shock force based on the input force at the tire, Fs being the force of the shock, FFT being the force of the tire onto the wheel hub. F of Bx and F of By is the X and Y from the knuckle onto the control arm. F of Ay and F of Ax being the force of the chassis onto the lower control arm. F of Cx, F of Cy, F of Dy, and F of Dx from the force from the lower control arm and the upper control arm, and F of T is the force of the top. So the governing equations are the spring force F equals K delta X, and the impact force, which is W equals F max for this specific, it was supposed to be delta Y, that's typo, sorry, delta Y equals A. So after I did my analysis, I came up with the first graph, which is an input force versus the output force. The input force being the force from the wheel, and the output force being the force that the shock exerts after inserted onto it. Then I conducted MTS shock test, which is a static static load test onto the shock, and I compared the effects of that force on two different PSIs. For the 35 PSI and the 40 PSI, the shock at the force that is exerted onto it would not be sustainable to hold, so it would bottom out, and we don't want that for the system. For the 45, it would bottom out as well. For the 50, the 55, and the 65, it is feasible to use these as settings because they can take that force. Of course, there is a downside to going with more stiffness. As you increase the stiffness, the natural frequency increases by 11% for each 5 psi. So for my status summary, I'll be proceeding with the mountain bike shocks. I've established a range for the desired ride height, which is 45 psi, 50 psi, 55 psi, 60 psi, and 65 psi. And I will choose the final setting once I find the damping coefficient based on impact. And to the right of this, on the right, this was based on the impulse. I did a vibration response based on the impulse from that drop. However, this is incorrect because I used a constant coefficient of damping and a constant coefficient of stiffness, which is not the case because the coefficient of stiffness is exponential, and the coefficient of damping is also what? How the coefficient?
The variance.
Yeah. The stiffness coefficient, the damping coefficient,
No, only the stiffness is.
the K?
Yeah, the K. It's exponential. It's not linear because of the air on the finish of the shocks.
If you go back to your plot, where are you? What are you saying, like those outer limits?
Yeah.
Now, I would argue, yeah, at the end of it, but if you kind of stay within the middle range, you can approximate that linear. So you could make your life easier and just say, I'm going to approximate this kind of linear. Worst case, obviously, it's going to not, but take this slope up the top off of end, you have a pretty linear effect.
That's what I did for the graph.
Yeah.
I took the average of it, but I wasn't sure if that was correct.
Yeah. Don't take the average because you don't want to account for those upper limits. Anywhere between 0.3 to 1.5, maybe 1.6, I would approximate that as a linear curve.
Okay.
Granted, type of extreme limits, like you have these non-linear effects, but ultimately for typical travel lengths during a traverse, you're not going to have this extreme situation. Maybe on an impact, but if you're looking for, if you want to measure or quantify damping coefficient, you just base it on some typical displacements. Stay in that linear range, you get a coefficient.
Thank you.
Also, for future, you've done several pieces of PSI, put all those curves on one plot, so you can put a different color so you need to compare. Because then it'll make life a lot easier to talk and show positive effects. Right now, they have similar shape, what's changing is the axis. So it's hard to make that comparison, especially if they have different ranges of axes. So you put them all on one plot, it's easier to compare.
Next, I'll be moving on to shock mounts. The objective for this is to create a shock mount that will endure the maximum spring force that the shock exerts, which was established as 500 pound force. And that's what it should endure from a drop of 1 meter. And it has to also allow for the geometry of the shock to fit within respect to the lower control arm and the placement of the chassis, which is 7.48 inches. That's the length of the shock. And the baseline design is an invertation. So for the design parameters is the load acting on the shock, which is the spring force and the placement on the chassis, the length of the shock with respect to the lower control arm, which I mentioned at 7.48. For the performance criteria, I've decided a factor of safety between 1.2 and 1.5. I'll get into that later. And for the evidence of baseline feasibility, I did a free-body diagram of the forces of the shock acting on each side, since the shock mount will take the force of both of the shocks. So for the worst case scenario, it's taking 500 pound force from the right and 500 pound force from the left. But in another scenario, it could be taking 500-pound force from the right and only 50-pound force from the left, assuming the wheel is up here and other wheels down there. For this, I fit the line and I got the, it's called the equation to find the forces that would exert, and for all of them again. And then for my factor of safety, I've gone with the factor of safety of between 1.2 and 1.5, and it has to take an axial, I believe it's an axial load of 500-pound force on each side. And the reason that I have gone between a 1.2 and 1.5 is if I went from 1.5 to 2, that's a 33% increase in the weight of the part. So for my status summary, I've gone with an inverted A shock mount with a factor of safety between 1.2 and 1.5 to ensure the safety of the suspension of the system, and I just have to complete my routing system.
What was your assumed thicknesses?
1.2.
That's what you're gonna have to look at, and that material think that the load. You'd rather shock than take it, but what about the mount? The mount take it? That hasn't been proven. So the shocks can be fine. You gotta make that mount not fit.
So I'll be discussing the wheels. So the problem description for the wheels is that I must be able to construct a wheelbarrow in which the tire will mount on, and at the same time reevaluate the dimensions of the current setup. It must also provide an adequate ride height and stiffness. It must be able to reduce weight but without compromising performance, and there shouldn't be any slippage between the wheel and the tire. So some of the design parameters that go along with the wheel is the dimensions, such as the length and thickness of the barrel, the tire properties such as the material selection of using polyurethane, the stiffness of the tire, and the pressure. And we must also take into consideration the static coefficient between the wheel barrel material and the tire material. So the performance criteria is that the wheel should be able to withstand a max expected load of 60 pounds, any internal and external pressure, and moment stat in my experience. The frictional force must be able to overcome the 3-pound drive shaft force, and any expected max stress on the wheelbarrow should not surpass the yield strength of the material.
So we're gonna see factor of
Not necessarily. For my safety factor, I have yet to calculate that.
what are you gonna design to?
So the end goal is to have not a large safety factor, but it should be large enough so that it has a high life cycle so that it can keep their strings as long.
Hear about life cycle, it's way high.
Way up.
That's again, because right now I see the big design of failure, not a life cycle.
I guess we evaluate that last.
And has to be safe factor greater than 1. That's what that policy statement says. The first we go through the design requirements, it's not performed here. So if you use a requirement, you have to meet that.
So I'll take this. So the evidence of baseline capability for the wheel is first looking at the drill holes where the spokes will mount onto. Each drill hole will experience a bearing stress induced by the weight of the rover and forced by the drive shaft, which will be 1,128 psi and 86 psi into their respective axes. The group stress is any external or internal pressure acting normal to the surface of the wheelbarrow. So we must first calculate the average force caused by the pressure applied onto the wheelbarrow, which leads us to the pressure times the outer radius divided by the thickness of the wheelbarrow. Next, we'll look at the forces caused by the spring, stiffness of the tire, plus any impact that may be induced while it's traversing, which is simply both forces added together divided by the cross-sectional area. And similarly, we could determine the stress by the weight and any centrifugal forces. And our governing equation is the internal minus external stresses, which leads us to about 2,608 psi. And my apologies for not including a three-line diagram, so I'll try my best to describe the force acting on this in order to determine the frictional force. So we know that if, let's say, the fork or the wheelbarrow is rotating clockwise, caused by the drag shaft force, then looking at the bottom contact point between the wheelbarrow and the tire, we can determine that the force by the drag shaft is acting toward the left. So we know that in order for the stiffness to not appear, the force must be opposing that force of the drag shaft, so it's going towards the right. And we know that frictional force is dependent on the normal force. So in order to calculate the normal force, we will look, for example, on the very bottom contact point between the tire and the barrel. The tire is exerting force by pressure. It's exerting the pressure and shear stiffness onto the wheelbarrow, and the wheelbarrow is exerting no force opposing those two forces. And substituting everything in, we get a frictional force of 80 pounds, which is 300 traffic force. Therefore, we do that there should not be any slippage happening. So FP is the average force caused by the pressure of the tire acting on the wheelbarrow. And then ST is basically the spring force by the tire onto the wheelbarrow, as it is like when the weight of the road contracts the tire acts because of the spring pushing back up. So that's just a resistance force of the tire by the road, by the weight of the road dragging.
But you're looking for the forces to be normal direction, right?
Yeah.
Not the ground, the contact path?
Yeah.
Why not just look at the weight of the road?
The spring force takes account of the weight of the road. So the more weight is acting on the tire, the more spring force exerts onto the wheelbarrow. Our main focus is the wheelbarrow.
So the spring force. Where is this pressure average for a swing?
It's coming from
So now, is that the force on the barrel, or is that the force on the outer wall of the tire?
force acting by the
Okay.
tire.
By the tire.
Yeah.
But on the wall of the tire, on the contact, if you go back, I would argue that the sum of FP average and the spring force should sum up to the weight of the rover. What would happen is that the tire would deform to account for the balance of pressure in the tire, so that the pressure force balances out with the weight of the rover. In essence, if there's more weight on a tire, to maintain the pressure inside the tire, you get a bigger contact point. Because you need a bigger force there. You have the same pressure, the tire will form, so after P times A, you get more A, for the same P, you get more F. That's just more load on that one tire. However, it's still the weight of the rotor. Like this is telling you, I need to tell Arrow about this on the formula, because if you put more pressure on the tires, that means you have more of a force pushing you down. I mean, you have more of a reaction force. So that's basically a downforce due to pressure on the tire, which is not realistic to me. So the sum of those two forces is basically just the weight of it. Like, however, they shift values between them, or not only that, I would say you have to follow the load path. Because the tire will take the contact and transfer that load. Normal force acts on the tire, which acts on the barrel, which acts on everything. But I think you have to follow the load path, not acting at the same point, or the same body. So those two should be the weight of the rotor. The problem right now is you're creating downforce by adding pressure to your tire, which is not. All you're doing is reducing the contact by increasing pressure. So your abnormal. So right now you have a friction force of 800 pounds. What is your friction coefficient? 0.8. So you're basically those two, on one tire you have 100 pounds on the tire. One tire should take 60 pounds. So 60 pounds times 0.8. You're looking at a much smaller value. You have 48 pounds. This is 80 pounds. So I'm saying I think those two numbers are not correct. You gotta look at the weight distribution of the wheel onto the ground. Yeah, because I don't know where these two numbers come from. It's just the weight. It's just all these different load paths at the end translate to the weight of the rotor on the tire. You just treat it as a rigid body and then say, what are the forces supporting the weight of the rotor? With everything happening in between, you care about the whole body at that contact. That's what you're looking at, the contact. So what is that force look like? It's just the weight of the rotor. Plus, you guys don't have any aero packages, so there's no more added force to it. That's it. You may have to look at the CG placement to know what tire is going to take the least amount of load. Worst case scenario, which tire is going to be slipping. If the moment arm is moving, if the robotic arm is moving to different places so that you're no longer at a 50-50 split. But worst case, let's say at a 70-30 split, then you have a lot less pounds. You have to determine your rotor weight for 120 pounds. Divided by 4, it's 30 pounds per wheel. That friction force gets a lot smaller real quick. And then if you shift the arm back, that will put some tires are going to have even smaller weight on it, so less friction. So there's no way to get 80 pounds of friction per tire. No way. Your rotor is weighing at least 300 pounds. So that's your true per tire. Per tire. And that's 320 pounds of friction, of traction that we have. And then divide that by 0.8, you're probably looking at 400 pounds rotor. And I know you don't have a 400 pound rotor.
I just have to recalculate
Your friction force should be about 24 pounds per ton. Assuming 120 pounds, even distribution, 30 pounds times 20, you're about 24 pounds. So that should be more realistic. And we'll start looking at extreme cases.
stress. We know that shear stress is induced by any torque acting on the wheel bearing. So in this case, the two torques are the drive shaft and the opposing friction force, which leads us to a total shear stress of about 2,157 psi. And for status summaries, we have so far conducted a drop test to determine tire spring stiffness, but we are continuing to conduct another one to validate those results. For accurate ride height, we will continue to use 19-inch tires, and I'm still continuing on calculating acting on the component in order to determine the factor of safety, and then begin reducing material more effectively.
So for the control arms, the objectives are to be able to withstand the forces of loading to current out of the competition that we will see, and to increase the tire's contact path going on over the road range. The requirements are for these is serviceable, and the baseline design was chosen because two of the control arms that's the way for the design parameters, some of the more requirements are for to maintain simple maintenance to allow for the integrate easily with all the respective components, and to use pins to act as mechanical joints. And some of the parameters are going to be to change the thickness and outer diameter of the tube to allow for it to achieve the first objective, and to change the length of the up control arm to allow to achieve the objective number 2. Some of the performance criteria are that it needs to have the safety of greater than 1.2. It needs to have a low mechanical range of less than or equal to 1 if you don't want any input forces being magnified to the rover. And the weight must be less than last year's design, which was 0.49 pounds, and our target is weight reduction of 0.39 pounds. Per control. This is per control. Okay, so this is the process I chose to start the ideal tubuling. I started with calculating the allowable bending stress based on material properties. I next determined forces and the resulting moments of the forms. After that, I started to take tube diameter and thickness and calculate the allowable bending stress. First, starting with the smallest tube size possible to keep the weight as low as possible. Next, I compared the bending stress to the allowable stress. If the bending stress was greater than the allowable, then it would fail, therefore we need to reach the diameter and use calculate the results. Once the bending stress is less than the allowable, I would use that tube size. Based on yield strength over So next, I compared I started with A513. So if I'm looking at all the different sides of variable, it was kind of limited in selection. So I also had to consider AC4130. For A513, its allowable yield strength was 60 psi, and for 4130 was 52.6 psi. And then, so next I compared all the different worst case scenarios. The scenario that had the largest moment was the scenario that rover hit a object or rock or something traveling at about 2 miles per hour, which is going to be the highest speed we might actually encounter during the competition. And that moment came out to be 7,062 pound-inch. Then knowing the moment, I was able to calculate bending stress based on all the different tube sizes, and I got this result. As you can see, the outer diameter of 0.375 inches with a thickness of 0.049 inches had a bending stress less than the allowable for 513 and 4130. And since it's available in 513, I chose that because 513 is higher in yield strength. Here's a chart of kind of all the specific numbers. As you can see, the two sides I've chosen, they had a bending stress of 52.1 psi. The factor of safety came out to be 1.34, and its weight was 0.423 pounds, which is less than last year's design of 0.49, but slightly above our target goal. Oh no, I had to take care of something. All right. Next, I consider the mechanical advantages of control lines, taking the derivative of I still I'll need to conduct FDA analysis on the control arms and do experimental testing. And after that, I'll need to also determine the length of the control arm to allow for
Alright, I might as well be going over the motors. So for our problem description, we're going to be determining whether or not the motors that we have on the current system are able to maintain and be sufficient enough at competition based on the given scenarios that are going to be at competition. I'll get into those later. So for our design parameters, we know that the weight of each wheel is going to be 5.5 pounds. The maximum friction coefficient of gravel, this is for kinetic coefficient, is 0.5. This was provided by the life science team. Thanks, William. And we also know that the rover will be on Earth, so the gravitational acceleration is just going to be similar to that of Earth, and it's going to be designed for that. And the races is going to be 9.5 inches. We also know the stall torque, the maximum RPM, and also the voltage and current from the spec sheet, and I'll get into those and how they apply later. So for our performance criteria, we want to make sure that our rover can maintain a max velocity of at least a minimum of 3 to a maximum of 8 miles per hour, while being able to tackle any terrain in the Utah desert. We also want to make sure that it's capable of traversing up to a 60-degree incline, because that's going to be one of the challenges that the rover has to complete. So, it's Photoshop. So. Yeah, it's okay. Alright, okay, so for our evidence of baseline visibility, we're going to be analyzing the gearbox. So for the gear ratios, this is provided by the gearbox made for manufacturers. The first gear ratio is going to be 2.25 to 1, and the second is going to be 16 to 1. This in turn gives us a total of a 52 to 1 total gear ratio. By utilizing this, we're able to calculate the maximum torque at stall. At stall, which would be about 64.68, so 5 people labor feet. We also can calculate the maximum RPM. The RPM of each motor is around 12,600, assuming that there is no load applied to being random maximum efficiency. This means that the gearbox itself can have an output RPM of around 242.3 RPM. The output velocity, disregard that number. That was calculated with the intent of tangential velocity, which is really what we're looking at. By calculating in terms of the velocity of the wheel itself, the rover itself can actually maximize at around 14 miles per hour. So for our evidence of baseline feasibility, one thing that we want to analyze and what we were looking to analyze this semester was determining whether or not our rover's motors have enough torque to allow it to make a skid turn. For this, we'll be analyzing it as it's going through a full 360-degree turn. And because of this, the wheels are going to be skidding in place as a result. So by looking at the free body diagram and summing up everything equivalent to 0, we're able to get our torque equation for the rover, for the wheels itself when it's skidding. We can compare this to the torque equation for the motors itself, which is power divided by omega times F, which is going to be our factor, well, a ratio factor between the actual and the rating torque. These will be determined through experimentation. And then for the 60-degree incline, what we did was we decided to break the rover into 2 components. First off the wheel, and then the second would be the chassis itself. For this, we're only going to be analyzing it with a constant velocity going up the ramp. For acceleration, that's still being calculated and the neural components for it. So because of that, the sum of the forces, some of the moments are going to be equal to 0. So for evidence of baseline feasibility, I decided not to just only use the kinetic friction coefficient of 0.5. I decided to do it between the minimum and the maximum kinetic friction coefficient presented at Utah. The minimum would be like 0.1, which is ice, which definitely not going to run into. And the maximum will be 0.7, which is concrete, and the rover isn't going to be doing any challenge tasks on concrete. But even then, we can conclude from here that it doesn't even reach like a third of what the stall torque is. So we can conclude from here that our rover can make a full 360-degree skid turn without having any issues. So for the incline going up a ramp, considering that we're going up, yeah. Yeah, the yellow is the stall torque and the green is the skid torque. And the skid torque was calculated from the equation on the top, UK times 1.0.
Is that assuming concrete?
The maximum kinetic friction coefficient for concrete is 0.7, and I did go up to that. We have 0 friction.
Yeah, I'm looking at your plot here, you have 0 as an option.
Oh,
And that's below fault slip.
that is true.
And then you have your maximum, again, still below fault slip. If
Yeah.
at 0, I have no friction. I can't see no matter how much torque I output, I can't propel myself forward. So there has to be some type of
Yeah.
resistance to it.
Let me clarify on that. That is a mistake. There is never going to be an instance where the kinetic friction coefficient is going to be equal to 0 in the
I know that's true, but if I'm looking at your worst case, 0, your best case, 0.7, everything is less than your stall torque. But my conclusion is this, even if it's like 0.1, low friction, then you can't get enough traction off of it. That's sort of I make myself feel like the way this is presented is kind of weird because what it's saying to me is you're going to be slipping the whole time.
Yeah, when it's making a full 360-degree turn, each of the wheels is going to be slipping, in a sense.
But if you're complete, you should have, is there a equal projection when you care about torque?
What do you mean, like, for instance, are you talking about like an arc turn? We're not looking at an arc turn. When the control team like controls the rubber, they only do it in a full 360-degree turn.
Yeah, but on the tire itself.
We haven't looked into that yet.
Right now, I'm kind of interpreting the data that it doesn't matter what surface you're on, you're not going to be able to use it.
Well, when it's turning, it's not going anywhere because it's going to be turning with
Yeah,
the
but I'm saying, well, they're not even going to be turning. The wheels are going to be spinning, and they're just slipping on the surface. Doesn't matter what it is. So if you push off the surface, it has to push back equally.
Wait.
And right now, what this is telling me is that the surface can't push back at the same time. Best case, we can push back at 24 pounds. Right? So, is that good?
Well, for our case scenario, it's way below the stall torque. And you are right that isn't going to be pushing, but bear in mind that the wheels themselves go.
You give it all the torque in the world, but it's not going anywhere.
Well, the thing is that the wheels are going to be spinning in opposite directions once making the turn.
You're not understanding what I'm saying. What I'm saying is that you're not going to go anywhere. You're not even going to turn. There's no directions happening. It's like if you're stuck in the mud and you're spinning tires, you have full throttle and it's not getting any traction. Or you're stuck in the mud or the sand pit. Something, you're just not getting any traction. That's what this is. I would expect to see some type of and then like, all right, that's anything above that we're good, anything below that we're not. That's sort of what I'm trying to get at. Right now, it seems you're gonna be slipping, doesn't matter what surface, but I know if you're on concrete, that rover is gonna turn. I think you have to, I would imagine if you're going, especially if you're going from 0, if these two will cross over somehow. So the friction coefficient has to be greater than X amount for us to be getting some traction. And given that the terrain has in this range, then we're good. But right now, it seems like it doesn't matter what surface you're on, you're not going to get any traction. No traction whatsoever.
Right. So for the rubber going up an incline, we're going to be looking at stagnation instead for this time. And this is assuming that the torque output for each wheel is going to be different. By utilizing MATLAB and plugging in the equations that we got from breaking up the two bodies, we get around 9 equations and 9 unknowns. This in turn gives us the maximum static friction coefficient that the ramp itself would have to be at before the rover begins to stall and is unable to move, and that's around 1.5. So as long as the static friction coefficient isn't at 1.5, the rover should be able to climb up the top elevations.
So there would be no weight on the parts.
This is moving up at a constant velocity. This is moving at acceleration. So for a status,
I'll follow that.
yeah, we're looking at the motor.
You said that best case, your friction coefficient is 0.7. Right, that's like concrete.
Well, no, that's kinetic friction. We're looking at static friction. Yeah. So when we're looking at static friction, that's just like a piece of. So with that being said,
So just in case there's any confusion on this, what we're talking about here is purely whether or not the motors are able to provide unnecessary skid force to turn and replace. Whereas on the next graph, where we're just considering.
We wanted this, like,
Essentially, yeah.
okay, that's what I was.
Because if we don't have facility, we're not essentially, the trick in terms of go back to the trick in terms of when the rover is turning about that central point has to do with the fact that we're not just experiencing we're not evaluating the friction of the tire spinning in the direction it's facing, but rather the tire dragging along the
lateral
Yeah.
point, okay.
Yeah.
I thought that was.
Apologies.
So for our status summary, we can conclude that the current motor set right now on the rover is suffice to tackle the terrain in Utah. What we do want to do is we do want to analyze the rover going up the incline at an acceleration, so we can conclude whether or not the motors are sufficient for that. For our next objectives, we want to run a torque experiment for the gearbox to obtain actual torque utilizing the band brake. This is a device that's provided by the 3068 lab, so we're going to be buying components for that, testing it. We also want to decide whether or not to switch out the current motors for longer lasting ones, depending on whether or not the torque output that we actually need is a lot less than like what the motors can supply. And then from there we can redesign the knuckles and the motor